In 1609, in the Italian city of Padua, Galileo Galilei lifted a narrow homemade telescope toward the night sky. His instrument magnified only about 20 times. Yet what appeared through that small circle of glass would disturb an ancient picture of the heavens. He saw mountains and shadows crossing the moon. Months later, he watched 4 tiny lights moving around Jupiter. These were worlds orbiting another world, something the old Earth-centered cosmos had never comfortably expected. But Galileo had arrived very late. For thousands of years before telescopes, mathematics, observatories, or even written language, human beings had already been watching those same wandering lights. So imagine that the glass disappears. The city fades away. You travel backward thousands of years until there are no observatories, printed books, clocks, or maps of the solar system. You are standing outside beneath a darkness modern people rarely experience. There are no electric lights beyond the fire beside you. The air carries the smell of smoke, damp soil, and vegetation cooling after sunset. Somewhere beyond the firelight, insects pulse steadily in the grass. Perhaps water moves quietly nearby. Above you, the sky seems enormous. Thousands of stars stretch from horizon to horizon, bright enough to cast faint impressions upon the landscape. A pale band crosses the darkness, although you have no idea that you are looking through the crowded disk of your own galaxy. You do not know what a galaxy is. You do not know that Earth is a planet. You certainly do not know that 8 major planets circle a star called the Sun. Yet you are already an astronomer in the simplest possible sense. You look up. Long before humans understood the solar system, they learned that the sky possessed rhythms. The sun appeared each morning, moved across the heavens, and vanished beyond the opposite horizon. The moon behaved differently. Its shape slowly changed, disappearing into darkness before returning as a delicate crescent. Night after night, it moved against the background stars. Then there were stranger lights. Most stars seemed to preserve their patterns, but several bright objects wandered through them. Their motion was slow enough to escape casual attention, yet obvious to anyone watching patiently across many nights. These wanderers were the planets visible without telescopes. Mercury could appear close to the horizon, often difficult to catch through haze and twilight. Venus was dramatically brighter, shining before sunrise or after sunset with an almost unnatural intensity. Mars carried a reddish color. Jupiter appeared brilliant and steady. Saturn moved more slowly, quietly shifting among the stars over months and years. Nobody watching them understood that these points were enormous worlds reflecting sunlight. Still, generations of observers learned their personalities remarkably well. The heavens became a kind of calendar for communities dependent upon hunting, gathering, farming, fishing, or seasonal migration. Knowing when conditions would change could matter enormously. The sky offered clues. Certain stars returned to particular positions during particular seasons. The rising and setting points of the sun shifted gradually along the horizon throughout the year. Even without understanding Earth's orbit, careful observers could recognize these repeating patterns. You might notice that one familiar group of stars disappears for part of the year. Months later, it returns to the morning sky shortly before sunrise. That return can become a seasonal marker. Memory becomes tradition. Tradition becomes knowledge. Archaeologists have discovered prehistoric structures whose orientations appear connected with significant solar or lunar positions. Some alignments are persuasive, while others remain disputed because ancient builders left no explanations behind. Researchers still debate how much astronomical intention should be assigned to particular prehistoric monuments. That uncertainty matters. A stone pointing toward a solstice sunrise might represent deliberate astronomy, ritual symbolism, landscape geometry, coincidence. or several purposes woven together. Ancient people rarely separated practical knowledge from spiritual meaning as neatly as modern categories sometimes suggest. The sky could tell you when winter approached, while simultaneously containing ancestors, spirits, animals, or divine stories. One did not necessarily cancel the other. Consider the moon. Its repeating phases provide one of nature's most obvious measures of passing time. A lunar cycle lasts about 29.5 days, conveniently close to what later societies would call a month. You do not need mathematics to notice it. You need patience. You watch the thin crescent grow toward fullness, then slowly diminish again. After enough repetitions, the pattern becomes reassuringly familiar. Occasionally, however, the familiar sky behaves badly. The moon darkens during an eclipse. More dramatically, daylight itself can disappear when the moon crosses directly before the sun. Birds may become quiet, temperatures can fall, and familiar surroundings acquire an eerie twilight. Imagine experiencing that without knowing celestial mechanics. The warmth on your skin weakens, shadows change. The world suddenly feels uncertain. Different societies developed different explanations for eclipses, and many associated them with supernatural danger or cosmic disturbance. Yet repeated observation also revealed something important. Even frightening celestial events possessed patterns. This realization would eventually become one of astronomy's deepest habits. The universe may surprise you, but careful observation can uncover regularity beneath surprise. There is another charming detail hidden in humanity's earliest relationship with the heavens. People did not merely watch the sky. They decorated themselves with it. Possible astronomical markings appear on ancient artifacts, bones, discs, and carved objects. Although interpreting these designs can be difficult, a cluster of dots might represent stars, counting marks, decoration, or something entirely different. The temptation to recognize constellations everywhere is surprisingly modern. Sometimes a dot is simply a dot. Still, unmistakable evidence from later cultures shows that celestial patterns became deeply woven into human imagination. Stars were connected into animals, heroes, tools, boats, and supernatural beings. The patterns differed from culture to culture because constellations do not actually contain lines. Human minds draw those lines across enormous distances. That makes the night sky partly physical and partly human. The stars exist. The pictures belong to us. As communities grow larger and agriculture becomes increasingly important, watching the heavens becomes more systematic. Seasonal timing influences planting, harvesting, travel, ceremonies, and the organization of communal life. A knowledgeable sky watcher becomes useful. You begin recording observations, perhaps first through memory, then through marks, monuments, and eventually writing. Thousands of years later, another kind of observer will inherit this patient habit. In Mesopotamia, generations of specialists will record planetary movements across clay tablets. Egyptian observers will connect celestial cycles with calendars, agriculture, and religious life. The wandering lights will receive names and histories. Much later, Greek thinkers will ask whether their motions can be explained geometrically rather than only symbolically. But those developments are still waiting beyond the horizon. For now, you remain beneath the prehistoric sky. You feel cool, ground beneath your feet, and warmth from the nearby fire against your hands. Smoke rises slowly before disappearing into darkness. Mars continues its silent journey. Jupiter shines without revealing its moons. Saturn appears as an ordinary point of light, hiding magnificent rings that no human eye can yet resolve. Every world is already there. The planets are moving around the sun, according to physical laws that humanity will require thousands of years to understand. Earth itself travels through space, while everyone standing upon it feels perfectly still. That is perhaps the quiet beauty of this beginning. The solar system does not wait to be understood. It turns regardless. Planets orbit. Moons circle planets. Comets return from distant darkness. Asteroids follow ancient paths left over from the formation of worlds. And beneath all of it, a small species begins doing something extraordinary. It notices. At first, you notice simply because the sky is beautiful, useful, frightening, and impossible to ignore. Then you begin remembering where the lights appeared yesterday. Eventually, someone asks why they move. That small question will take humanity from campfires to observatories, from naked eyes to telescopes, and finally to machines traveling between planets. But before anyone can understand the wandering worlds, someone must first learn to record their wandering. Far to the east of the Mediterranean, beside great rivers and growing cities, that patient recording is about to become remarkably precise. The sky is becoming more than memory. It is becoming data. By the time people begin building cities between the Tigris and Euphrates rivers, the night sky has become an old companion. You can imagine yourself standing on a flat rooftop in ancient Mesopotamia after the heat of another long day. The mud bricks beneath your feet still hold a little warmth. Cooking fires leave a faint smell of smoke and grain in the evening air. Below, animals shuffle through narrow streets, while distant voices soften as darkness settles over the city. Above everything, the familiar lights return, but now you are doing more than watching them. You are recording them. In ancient Mesopotamia, especially among Babylonian scholars, astronomical observation gradually developed into an extraordinarily systematic tradition. Generations of observers tracked the moon, eclipses, stars, and the wandering planets across long stretches of time. Their records transformed the sky into something that could be compared. Tonight could be measured against last month. This year could be compared with previous years. Patterns once preserved mainly through memory could now survive the people who first noticed them. Clay helped make that possible. A scholar could press wedge-shaped marks into a damp tablet, recording celestial events before the clay hardened. It hardly resembles a modern observatory notebook, but its purpose could be surprisingly familiar. Where was Jupiter? When did Venus disappear? When did an eclipse occur? Patient repetition gradually revealed order. Babylonian astronomical diaries eventually contained observations of planetary positions, lunar behavior, weather, commodity prices, and other events. To modern eyes, this mixture may seem peculiar. To Babylonian scholars, heaven and earth belonged to a connected world of meaningful signs. Astronomy and astrology were not yet separate disciplines in the modern sense. A strange planetary appearance might be interpreted as significant for a king, a harvest, or the stability of the realm. Yet practical prediction emerged from this framework. The observers became extremely skilled at recognizing celestial cycles, even when their explanations differed greatly from modern astronomy. That distinction is important. You do not need to understand gravity to predict a repeating pattern. You only need careful records. Babylonian astronomers became particularly accomplished at predicting lunar phenomena and recognizing cycles associated with eclipses. They also developed mathematical techniques for describing changing celestial positions. Instead of constructing a physical model showing what planets actually were, they could calculate where wandering objects were likely to appear. The sky was becoming numerical. Venus received especially close attention. Its appearances before sunrise and after sunset create a striking rhythm because Venus orbits closer to the Sun than Earth does. Of course, an ancient observer does not know this geometry. You simply notice that the brilliant object repeatedly appears, disappears into the sun's glare, then eventually returns. One famous set of records describes observations associated with the appearances of Venus across many years. Scholars continue debating how reliably parts of these records can be used to establish exact ancient chronologies. Even an old astronomical observation can produce a very modern academic argument. Some things remain reassuringly constant. Farther southwest, along the Nile, Another civilization is developing its own intimate relationship with the heavens. Imagine arriving in Egypt before sunrise. The desert air feels unexpectedly cool against your skin, while the river carries the smell of wet vegetation and dark mud. Beyond cultivated fields, the landscape becomes dry and pale. Then the eastern horizon begins glowing. For Egyptian communities, the sky was connected closely with timekeeping, religion, agriculture, and the rhythms of the Nile. The annual cycle of the river shaped life profoundly. Celestial observations helped organize calendars and religious activities within that changing landscape. One particularly important star was Sirius, the brightest star visible from Earth. Its seasonal reappearance in the morning sky became associated with the Egyptian calendar and the approach of the Nile's inundation. The relationship was not perfectly simple across every period because calendars drifted and environmental timing varied. Still, the connection became culturally powerful. You can understand why. After weeks when Sirius has been hidden in sunlight, its return shortly before dawn feels almost theatrical. A brilliant point emerges from the brightening horizon. Soon afterward, an entire agricultural world enters another seasonal phase. The heavens seem to announce events below. Egyptian astronomy also served architecture and ritual. Certain structures were oriented toward celestial directions or significant positions in the sky. Although scholars debate the exact astronomical intentions behind some individual alignments, the pyramids naturally attract especially enthusiastic theories. Some proposed relationships are supported by serious archaeological investigation. Others require considerably more imagination. Ancient Egypt has never suffered from a shortage of imaginative explanations. What matters is that Egyptian specialists genuinely possessed sophisticated methods for observing stars and organizing time. Groups of stars helped divide the night into intervals. The changing sky functioned as a clock long before mechanical clocks existed. You lie awake beneath a dark Egyptian sky and watch one stellar group rise. Later, another appears. Its arrival tells you that part of the night has passed. Time is written overhead. Meanwhile, other civilizations across the world are developing their own celestial traditions. In China, long-running astronomical observations would eventually preserve records of eclipses, comets, planetary events, and temporary stars. Across the Americas, societies developed calendars and architectural orientations connected with solar and other celestial cycles. Different communities watched different horizons, but everyone inhabited the same solar system. None could yet see its architecture. To the naked eye, the planets do not obviously circle the sun. Indeed, their behavior can look unnecessarily complicated. Mars provides a particularly troublesome example. Night after night, it normally moves slowly against the distant stars. Then, at certain times, it appears to slow down. It stops. It moves backward. Eventually, it reverses direction again and resumes its usual path. Today, you call this apparent retrograde motion. From a moving Earth, the effect becomes understandable as Earth overtakes another planet in its orbit. But without knowing that Earth moves, the behavior is deeply puzzling. Imagine trying to explain it while standing on apparently motionless ground. Nothing feels as though it is traveling around the sun. There is no wind caused by enormous orbital speed. No vibration announces Earth's rotation. A dropped object falls straight downward rather than flying away behind you. The evidence available to ordinary experience strongly suggests stability. So early cosmologies placing Earth in a central or special position were not foolish guesses. They were attempts to organize what human senses actually reported. The great conceptual difficulty would be learning that your senses reveal only part of the story. For now, however, explanation remains secondary to observation. Across generations, people accumulate records of where celestial objects appear and when particular events repeat. The planets acquire identities because each behaves differently. Mercury remains elusive near twilight. Venus dominates mornings or evenings. Mars sometimes burns with unusual reddish brilliance. Jupiter moves with stately brightness. Saturn requires even greater patience. These differences encourage stories, associations, and eventually mathematical questions. You stand once more beneath the stars, but the sky has changed in one subtle way. Not physically. The planets continue along the same ancient orbits. The change has happened inside human thought. A wandering light is no longer merely something noticed. It has a history of positions. It can be compared, calculated, and sometimes predicted. Once humans discover that the heavens can be measured, another question quietly becomes unavoidable. What arrangement of worlds could produce these strange motions? Around the Mediterranean, philosophers and mathematicians will soon begin proposing answers. Some will place Earth firmly at the center. One remarkable thinker will place the sun there instead, and the wandering lights above you will slowly become worlds. You now move westward toward the Mediterranean, where generations of Greek thinkers inherit a sky already crowded with observations, calendars, stories, and difficult questions. On a clear evening, you might stand beside a harbor as sunlight fades across the water. Wooden ships creak against their ropes. Salt hangs in the air, mixed with smoke from cooking fires and the sharper smell of fish brought ashore earlier that day. Above the darkening sea, Venus appears. The same brilliant wanderer, watched from Babylon and Egypt, now shines over Greek cities. But some observers begin asking a different kind of question. What if the heavens can be explained through geometry? This change does not happen suddenly. Greek astronomy grows from contact with older traditions, especially knowledge developed in Mesopotamia and Egypt. Ideas travel with merchants, sailors, conquerors, scholars, and manuscripts. No civilization studies the heavens entirely alone. Yet Greek philosophers increasingly search for physical and mathematical arrangements capable of explaining what observers see. The question becomes not merely when Mars will appear. They want to know why it moves. Early Greek thinkers proposed many different cosmic systems, some stranger than others. Earth might float upon water, rest within a spherical cosmos, or occupy a privileged position surrounded by celestial circles. Gradually, one idea became especially influential. Earth was spherical. This conclusion did not require photographs from space. Observers could notice that Earth's shadow during a lunar eclipse was curved. Travelers moving north or south also saw familiar stars change height above the horizon. Some constellations disappeared entirely, while others became visible. These observations made sense on a curved surface. By the 4th century BC, Aristotle offered arguments supporting a spherical Earth and a structured geocentric cosmos. Earth remained motionless near the center. The moon, sun, planets, and stars belonged to surrounding celestial regions. To you, accustomed to seeing diagrams of planetary orbits, this arrangement seems backwards. From Aristotle's position, however, a stationary Earth was quite reasonable. You feel no enormous motion beneath your feet. A stone dropped from your hand lands near the place directly below it. The stars seem to rotate around you each day. The ground feels solid. Earth certainly behaves like the thing that stays still. Aristotle also distinguished the changing earthly realm from supposedly more perfect heavens. Celestial motion was associated with circles, which Greek philosophy often regarded as especially harmonious forms. This preference would influence astronomy for many centuries. Nature, unfortunately, had not agreed to make planetary orbits perfect circles. That awkward detail was still waiting. Before reaching it, you encounter one of antiquity's most remarkable measurements. Around the 3rd century BC, Eratosthenes attempted to estimate Earth's circumference. He compared the sun's position at 2 Egyptian locations and used geometry to infer the size of the planet. The exact details of his procedure and the length represented by his measurement units remain subjects of scholarly discussion. Still, the underlying method was brilliant. You can measure an entire world without walking around it. All you need is sunlight, distance, geometry, and careful thought. Earth was becoming measurable. Once Earth could be treated as a physical sphere, its place within the larger heavens could also become a mathematical problem. Then comes Aristarchus of Samos. Living during the 3rd century BC, Aristarchus proposed something extraordinary. Earth moves around the sun. He also argued that Earth rotates on its axis. Suddenly, the daily motion of the heavens could be explained partly by Earth's own turning. The sun, rather than Earth, occupied the central position in his known planetary arrangement. You might expect everyone to celebrate. They did not. Heliocentrism created serious observational problems. If Earth moves around the sun, nearby stars should appear to shift against more distant ones during the year. This effect is called stellar parallax. Ancient observers could not detect it. There was a possible answer. Perhaps the stars were unimaginably distant. That solution was physically possible, but it demanded a cosmos far larger than many people found plausible. There were also philosophical objections concerning motion and the nature of Earth. A moving Earth needed explanations that ancient physics could not yet provide convincingly. So Aristarchus had offered a powerful possibility without enough evidence to make it dominant. Historians continue discussing how completely his original system can be reconstructed because much of his heliocentric work survives only through later references. An idea can be revolutionary and still leave frustratingly little paperwork. Most astronomical work continued within broadly geocentric frameworks. This did not prevent impressive progress. During the 2nd century BC, Hipparchus became one of antiquity's most important observational astronomers. He compiled celestial positions and developed mathematical methods for analyzing the heavens. He also investigated the lengths of the year and month with considerable precision. Perhaps most remarkably, Hipparchus recognized a slow change in the celestial coordinate system, now known as the precession of the equinoxes. Earth's rotational axis slowly changes direction over thousands of years. To Hipparchus, the physical reason was unknown. Yet by comparing observations across time, he could detect that the heavens were not maintaining exactly the same relationship to seasonal reference points. Ancient records had become instruments. A measurement made by someone long dead could reveal motion too slow for one lifetime to notice. This is one of astronomy's quiet powers. Time extends your eyesight. Hipparchus is also traditionally associated with an influential star catalogue, although scholars still investigate exactly how surviving evidence relates to his original catalogue and later compilations. Ancient texts rarely arrive with convenient version histories. Even so, measuring stellar positions represented another profound step. The sky was becoming a coordinate system, yet the planets continued causing trouble. Mars could move forward, pause, reverse, and then move forward again. Venus never wandered very far from the Sun. Mercury behaved similarly, but remained more difficult to observe. Any successful cosmic model had to reproduce these patterns. A simple set of circles around Earth was not enough. So astronomers added more geometry. One useful concept involved a planet moving along a smaller circle whose center itself moved around a larger circle. These combinations could reproduce complicated apparent motions while preserving circular movement. Later generations would call such smaller circles epicycles. They are sometimes portrayed as absurd patches invented to rescue a failing model. That description is too simple. Geometric devices like these could produce genuinely useful predictions. They were mathematical tools built around the best observational framework then available. And remember what you can actually see. When you stand beneath the Greek night sky, Earth still feels motionless. The heavens still appear to revolve overhead. Stellar parallax remains invisible. There are no telescopes revealing moons circling Jupiter. There are no observations showing the complete phases of Venus. There is no Newtonian mechanics explaining why a moving Earth does not leave birds and clouds behind. The geocentric universe survives because it fits much of the evidence people possess. It also fits influential philosophical ideas. That combination is powerful. Still, another possibility has already entered human thought. Somewhere among lost manuscripts and remembered arguments lies the suggestion that Earth is itself a wanderer. You leave the harbor beneath a sky that appears almost unchanged. Jupiter glows steadily. Mars continues its troublesome path. Saturn crawls against the stars with almost insulting patience. But human understanding has divided into competing possibilities. Perhaps Earth stands still. Perhaps Earth moves. Perhaps circles can explain everything. Perhaps the heavens are larger than anyone suspects. The debate will not be settled quickly. Instead, another astronomer will gather centuries of Greek mathematical astronomy into a system so effective that it will shape the human picture of the solar system for more than 1,000 years. His name is Ptolemy, and his universe will be beautifully complicated. You arrive in Alexandria during the 2nd century AD, when the Mediterranean world has already inherited centuries of arguments about the structure of the heavens. The city is busy even as evening approaches. Footsteps pass along stone streets. Merchants finish their work, and the smell of oil lamps mingles with salt drifting inland from the harbor. Above the rooftops, the first stars emerge. Mars is there somewhere. So are Jupiter and Saturn. Their motions have been watched for generations. Yet fitting those motions into one dependable mathematical system remains an enormous challenge. In this world, Claudius Ptolemy begins assembling an answer. Ptolemy was an astronomer, mathematician, geographer, and writer working in Roman Egypt. His great astronomical work gathered earlier Greek knowledge while developing a sophisticated mathematical framework for predicting celestial positions. Earth remained stationary near the center. Around it moved the moon, sun, planets, and the distant sphere of stars. Yet this was not merely a picture of nested circles. The mathematics became far more subtle. Imagine watching Mars over many months. Most nights, it drifts slowly in one direction, against the stars. Then its motion weakens. It seems to stop before traveling backward for a time. Finally, it turns again. A simple circle centered on Earth cannot reproduce this behavior accurately, so the model needs additional motions. A planet could travel around a small circle called an epicycle. The center of that epicycle simultaneously traveled around a larger path called a deferent. By combining motions, astronomers could imitate the strange loops traced by planets across the sky. Ptolemy introduced further refinements. Earth did not always sit exactly at the geometric center of a planet's deferent. He also used a mathematical device now called the equant, which allowed motion to appear uniform when measured from a particular point. The arrangement was ingenious. It was also complicated, but complexity alone does not make a scientific model useless. What mattered was whether calculations matched observations closely enough to predict where celestial objects would appear. Ptolemy's system often did. You could calculate future planetary positions, organize calendars, and anticipate celestial configurations with impressive effectiveness for the period. That usefulness helped the model survive. There was another reason. The geocentric arrangement matched ordinary experience beautifully. Stand outside and wait. You feel Earth beneath your feet. Nothing suggests that the ground is rotating at tremendous speed. Nothing announces that your entire world is rushing around the sun. Instead, the sun rises. The moon crosses the heavens. Stars turn around the sky. Everything seems to move around you. For an observer without modern instruments, that appearance carries considerable weight. Even so, the Ptolemaic universe was never as simple as saying that everyone believed Earth occupied the exact center because humans felt important. Astronomers were solving technical problems. They wanted numerical predictions. Philosophers could argue about physical reality, while mathematical astronomers concentrated on calculating appearances. Those goals sometimes overlapped imperfectly. Scholars still debate how Ptolemy himself understood the relationship between mathematical models and the physical construction of the cosmos. The surviving texts permit several interpretations. Ancient astronomers, inconveniently, did not write their books to settle arguments among historians 2,000 years later. One especially interesting feature of Ptolemy's work involves the order of the planets. The Moon was closest to Earth, while Mercury and Venus occupied regions associated with the Sun. Mars lay beyond the Sun, followed by Jupiter and Saturn. The fixed stars formed the distant outer realm. The true distances were unknown, yet the heavens had acquired structure. You could imagine yourself looking upward and mentally placing each wandering light within this layered cosmic machinery. Venus becomes particularly interesting. It never travels very far from the Sun in Earth's sky. Mercury behaves similarly. Any successful model must account for that relationship. The Ptolemaic system therefore linked aspects of their geometrical motions to the Sun's motion. The mathematics worked without recognizing that both planets actually orbit the Sun inside Earth's orbit. Reality was hiding inside the pattern. Mars offered a different clue. It becomes especially bright during certain retrograde periods. A heliocentric explanation eventually makes this natural because Earth is then passing relatively close to Mars. Geocentric mathematics could reproduce the apparent motion without revealing the underlying orbital arrangement. This difference between prediction and explanation will return throughout scientific history. A model may tell you where something appears. A deeper theory may explain why. For centuries, however, there is no decisive observation forcing astronomers to abandon geocentrism. Stellar parallax remains undetected. No telescope has shown the full cycle of Venusian phases. Nobody has watched moons orbit another planet. The old system therefore continues performing useful work. Meanwhile, Ptolemy preserves and expands another inheritance from earlier astronomy: star positions. Cataloging stars allows future observers to compare the sky across generations. A star catalog is not dramatic in the way a comet or eclipse can be dramatic. It is simply patient measurement. Yet patient measurement changes everything eventually. There is even a curious historical wrinkle concerning some of the observations underlying Ptolemy's star catalog. Researchers have long discussed how much material came from Hipparchus and how much resulted from Ptolemy's own observations or transformations. The question remains technically complicated. The ancient sky has become a detective story written partly in coordinates. Outside scholarly circles, ordinary people continue experiencing the heavens much as their ancestors had. Farmers watch seasonal changes. Sailors use stars for orientation. Travelers recognize familiar constellations. Religious calendars depend upon celestial cycles. Most people do not spend evenings calculating epicycles. This may be comforting. Even in antiquity, advanced astronomy could remain safely someone else's homework. Still, mathematical astronomy is becoming increasingly powerful. You can now separate two experiences of the same night sky. There is the sky you see. Then there is the hidden mathematical sky that scholars calculate. The second contains circles, offsets, angles, tables, and predicted positions. It cannot yet show what the planets physically are. Mars remains a point. Jupiter remains a point. Saturn gives no hint of its rings. Nobody knows about Uranus or Neptune. Asteroids remain invisible. Pluto lies beyond imagination. Even the known planets are vastly misunderstood in size and distance. Yet something important has been achieved. Human beings have built a mathematical machine capable of following wandering lights across generations. The machine is imperfect, but it works remarkably well. That creates a fascinating problem for anyone hoping to replace it. A new model cannot merely sound elegant. It must calculate the heavens at least as effectively as the old one. Centuries begin passing. Political powers rise and disappear. Languages change. Libraries are damaged, rebuilt, scattered, and copied. Ptolemy's astronomy travels through manuscripts rather than remaining frozen in Alexandria. Eventually, scholars working across the medieval Islamic world encounter this inherited mathematical cosmos. They translate it, preserve it, teach it, and test it. They do not simply place the old books reverently upon shelves. Astronomers measure again. Some find serious problems. New observational instruments grow larger and more precise. New mathematical approaches appear. Questions accumulate around Ptolemy's elegant machinery. You stand beneath another quiet night. The same planets continue moving. They are indifferent to every diagram made about them. Earth rotates unnoticed beneath your feet while carrying you around the sun. The old geocentric calculations still predict much of what you see. But prediction has begun producing dissatisfaction. A model can survive for centuries and still contain weaknesses. Sometimes those weaknesses remain almost invisible until enough observers measure carefully enough. And across the medieval world, that careful measuring is about to continue. Centuries pass, and you find yourself beneath another clear night, this time in the medieval Islamic world. The air is cooler after sunset. Stone walls slowly release the heat they gathered during the day, while oil lamps flicker in courtyards below. You smell smoke, dust, and perhaps ink from a nearby room where manuscripts are being copied. Above you, the planets remain unchanged. Human institutions have not been so fortunate. The political world surrounding the Mediterranean and Western Asia has transformed since Ptolemy worked in Alexandria. Empires have divided, cities have risen in importance, while others have declined. Languages of scholarship have changed, yet astronomical knowledge has continued traveling. Texts attributed to Greek astronomers and philosophers were translated, studied, criticized, and combined with knowledge from other intellectual traditions. Ptolemy's astronomy became especially influential. His great mathematical work reached scholars who wanted to understand celestial motions accurately enough to calculate planetary positions, calendars, directions, and times. They inherited a formidable system. They also inherited its problems. It is tempting to describe medieval Islamic astronomers simply as guardians who preserved ancient Greek astronomy until Europe rediscovered it. That description misses much of what actually happened. Preservation mattered enormously, so did translation. But scholars also checked measurements, improved mathematical methods, developed instruments, produced astronomical tables, and questioned aspects of inherited models. The heavens were not a museum exhibit. They remained a working problem. Imagine joining an observer on a rooftop or within an astronomical complex. There is no telescope. Your most important instruments depend upon carefully measured angles. An astrolabe can help determine celestial positions and solve practical astronomical problems. Quadrants and other instruments allow observers to measure altitude. Large observational devices can achieve greater precision because increasing their scale makes angular divisions easier to distinguish. Everything depends upon patience. You align an instrument with a star. Cool metal or wood presses against your fingers. Someone nearby records a number. Then you repeat the process, again and again. Astronomy remains wonderfully capable of making enormous cosmic questions depend upon somebody carefully reading a scale in the dark. One major center of astronomical activity developed in Baghdad during the Abbasid period. Astronomers conducted observations and produced tables intended to improve celestial calculations. Later, other important centers appeared across a vast region, stretching from Iberia through Persia and Central Asia. There was no single medieval Islamic astronomical tradition. Different scholars disagreed, borrowed from one another, and pursued different mathematical or philosophical goals. Among the influential figures was al-Battani, who worked around the 9th and 10th centuries. His observations improved measurements of solar and lunar motion and contributed to more accurate astronomical parameters. He also used mathematical techniques that would influence later astronomy. Centuries afterward, European scholars would encounter his work through translations. Knowledge continued migrating. Another important figure, Ibn al-Haytham, is famous especially for his work on optics. He also criticized aspects of Ptolemaic astronomy. The problem was subtle but important. Ptolemy's mathematical devices could reproduce observed planetary positions, yet some seemed difficult to reconcile with the expected physical structure of celestial spheres. A calculation could work, while its imagined machinery felt physically troublesome. That tension would not disappear. Other scholars tried to construct alternative geometrical arrangements that preserved successful predictions without relying upon some of Ptolemy's controversial devices. At Maraga, in present-day Iran, a major observatory was established during the 13th century. Imagine approaching it under a dry evening sky. The landscape is quiet, except for footsteps and low conversation. Inside, scholars work among instruments, manuscripts, numerical tables, and geometric diagrams. This is astronomy before electronic detectors. The human eye remains the sensor. Among those associated with Maraga was Nasir al-Din al-Tusi. He developed a geometrical construction, now commonly called the Tusi couple. By combining circular motions, the construction could generate an oscillating linear movement. It offered astronomers a clever way to reformulate parts of planetary theory. Later, mathematical similarities between such techniques and those appearing in European astronomy have produced long scholarly discussions. Historians still investigate the precise routes through which mathematical ideas may have traveled toward Renaissance Europe. Direct borrowing, indirect transmission, parallel development, and lost intermediaries can be difficult to distinguish. Manuscripts rarely leave travel diaries. The important point is broader. Long before Copernicus, sophisticated astronomers were already dissatisfied with elements of Ptolemaic planetary modeling. They were actively trying to repair them. Further east, another extraordinary observatory appeared at Samarkand during the 15th century under Ulugh Beg. There, enormous instruments helped astronomers determine stellar positions with remarkable precision. One great meridian instrument was built on a scale far beyond a handheld device. You can almost feel the architectural ambition behind it. Instead of bringing a small instrument beneath the sky, you make the building itself part of the measurement. Ulugh Beg and his collaborators produced an influential star catalogue and astronomical tables. The stars Ptolemy had measured many centuries earlier were measured again. Small differences mattered. Astronomy was learning that inherited authority could be tested against the heavens themselves. Meanwhile, ordinary people continued meeting astronomy in practical forms. Celestial observations helped regulate calendars and determine times connected with religious practice. Astronomical methods could assist with geographic orientation and timekeeping. Astrolabes became sophisticated tools capable of solving many problems involving the positions of the sun and stars. They could also become beautiful objects. Some surviving instruments are covered with delicate inscriptions and carefully engraved scales. There is something quietly charming about this mixture of mathematics and craftsmanship. A device designed to measure the heavens can also be made lovely enough to treasure. Yet the solar system itself remains hidden. Saturn is still only a wandering light. Jupiter does not reveal its moons. Venus does not openly display the phases that will later become devastating evidence against traditional arrangements. Mars continues its backward loops. Mercury remains irritatingly close to the horizon. The planets reveal motion, but not their physical faces. That limitation encourages mathematical astronomy to become increasingly elaborate. If you cannot travel to Mars or resolve its surface, you must infer its behavior from angles and time. This is difficult work. It is also preparing something important. Better measurements expose weaknesses that rough measurements can hide. More accurate tables make discrepancies noticeable. Criticism becomes possible because generations have preserved enough knowledge to know where the predictions fail. Across medieval Europe, astronomical traditions are also developing through monasteries, universities, courts, and growing contact with translated works. Latin translations make important Greek and Islamic astronomical texts increasingly available. Ptolemy returns to European scholarship, accompanied by centuries of commentary, mathematics, and criticism. The old geocentric cosmos therefore arrives not as an untouched relic. It arrives carrying questions. You can sense those questions accumulating as another century approaches. How should planetary motion be represented? Why do mathematical devices work when their physical meaning seems uncertain? Can a simpler arrangement explain the wandering planets? Most importantly, what if the assumption that Earth stands still is itself the problem? That possibility is ancient. Aristarchus had suggested a moving Earth long before. But an old idea becomes powerful only when someone can rebuild it into a complete mathematical system. In Renaissance Europe, a scholar named Nicholas Copernicus begins doing exactly that. He will not destroy the old astronomy overnight. He will borrow from it, rearrange it, and struggle with many of the same geometrical difficulties. Yet one change will alter the meaning of every planetary motion. Earth will become a planet. You look upward once more. Mars moves quietly against the stars. For thousands of years, humans have treated that motion as something happening above a stationary world. Soon, the ground beneath the observer will begin moving too. You enter the 16th century beneath a European sky that looks exactly as it did to Babylonian observers thousands of years earlier. Venus still follows the sun. Mars still wanders backward at intervals. Jupiter and Saturn continue their slow journeys through the constellations. Yet beneath that familiar sky, the intellectual landscape is shifting. Printed books can now spread ideas more rapidly than handwritten manuscripts ever could. Universities preserve older astronomical traditions, while scholars compare new calculations against inherited tables. Navigation also places increasing demands upon astronomy. Calendars, mathematics, and accurate measurements of the heavens. Into this changing world comes Nicholas Copernicus. Imagine him working late beside papers covered with circles, numbers, and geometric constructions. A candle gives off a faint smell of warm wax. Pages rustle beneath his hands. Outside, the evening air is cold enough to creep through stone walls. Copernicus is reconsidering a question almost 2,000 years old. What if Earth moves? His answer gradually develops into a heliocentric system. Earth rotates once each day and travels around the Sun each year. The other known planets also orbit the Sun. The Moon remains Earth's companion. This rearrangement produces an immediate conceptual reward. Retrograde motion becomes much easier to understand. Picture yourself moving along a track beside a slower traveler. As you pass, the other person briefly appears to drift backward against the distant landscape. Nothing has actually reversed direction. Your own motion created the appearance. Earth does something similar when overtaking Mars. Mars continues along its orbit, but from Earth's moving viewpoint, it temporarily traces a backward loop against the stars. The strange wandering suddenly has a natural geometric explanation. The brightness of Mars also makes greater sense, because Earth and Mars sometimes approach one another more closely. The ordering of the planets becomes clearer. Mercury and Venus stay near the Sun in our sky because their orbits lie inside Earth's orbit. Mars, Jupiter, and Saturn occupy progressively more distant paths. Earth is no longer the unmoving platform from which the universe is arranged. It joins the wandering lights. This is a profound change. Yet Copernicus does not immediately produce the modern solar system you recognize. He still values uniform circular motion. Because actual planetary orbits are elliptical, circles alone cannot reproduce observations perfectly. His system therefore retains combinations of circular motions and considerable mathematical complexity. Heliocentrism simplifies the architecture without instantly simplifying every calculation. Copernicus's major work appears in 1543, near the end of his life. Its reception is gradual and complicated. Some astronomers find heliocentric mathematics useful without accepting Earth's physical motion. Others object on philosophical, physical, observational, or religious grounds. There is still no detectable annual stellar parallax. If Earth travels around the Sun, why do the stars not visibly shift? Again, the answer could be enormous distance, but that requires accepting a vast gulf between Saturn and the stars. The universe must become much larger. There are physical questions too. If Earth spins, why are you not thrown away? Why does a stone dropped from a tower land near its base? Why do birds remain above the same landscape? A complete physics of moving reference frames does not yet exist. Copernicus has rearranged the heavens before mechanics can fully explain why the rearrangement works. Astronomers therefore need better evidence. That evidence begins with better measurement. Late in the 16th century, Tycho Brahe becomes perhaps the greatest naked-eye observational astronomer of his age. Tycho is difficult to mistake for a quiet background figure, a nobleman with immense ambition. He famously lost part of his nose during a youthful duel and later wore a replacement. Accounts differ regarding exactly what metals his artificial nose contained. Even planetary astronomy occasionally pauses for facial prosthetics. More importantly, Tycho built sophisticated observatories and assembled instruments capable of measuring celestial positions with exceptional precision before telescopes entered astronomy. On the island of Hven, he established Uraniborg and later Stjärneborg. Imagine walking among these instruments on a cold Scandinavian night. Your breath becomes faint mist. Metal feels icy beneath your fingers. Assistants move through dim light while someone reads angular scales with extraordinary care. There is no magnifying telescope. Precision comes from large instruments, careful calibration, repeated observation, and relentless attention. Tycho did not accept Copernicus's heliocentric universe. Instead, he proposed a hybrid arrangement. Earth remained stationary at the center. The Sun and Moon moved around Earth, while the other planets moved around the Sun. This Tychonic system preserved a motionless Earth while incorporating useful relationships revealed by heliocentric geometry. It also reminds you that scientific change rarely offers only two choices. People construct alternatives. Tycho's observations also challenged another ancient assumption. In 1572, a brilliant new star appeared in the constellation Cassiopeia. According to traditional Aristotelian cosmology, the distant stellar heavens should be unchanging. Tycho measured the object's position and found no detectable nearby parallax. That suggested it belonged beyond the Moon. Change had appeared in supposedly perfect heavens. Then, in 1577, a bright comet crossed the sky. Tycho's measurements again suggested that it traveled beyond the lunar region. More disturbingly, its path seemed incompatible with solid nested celestial spheres. The heavens were becoming physically less tidy. Tycho continued recording planetary positions with extraordinary accuracy. Among the objects he followed, Mars would prove decisive. Mars is troublesome because its orbit is noticeably more eccentric than Earth's. Small errors in a circular model become harder to hide. After Tycho's death in 1601, his observational legacy became crucial to Johannes Kepler. Kepler was a mathematician with a strong taste for cosmic harmony. He initially hoped planetary distances might fit an elegant geometrical scheme involving nested regular solids. It was beautiful. Nature declined the invitation. Working with Tycho's measurements, Kepler struggled especially with the orbit of Mars. The calculations refused to fit a perfect circle. A discrepancy of roughly 8 minutes of arc became famous in his reasoning. It was small. Kepler refused to ignore it. That stubbornness changed astronomy. He eventually discovered that Mars followed an ellipse, with the Sun located at one focus. The circle finally lost its ancient privilege. Kepler formulated 3 laws of planetary motion. Planets travel in elliptical orbits. They sweep out equal areas in equal times, meaning their orbital speeds change. A mathematical relationship also connects orbital periods with average distances from the Sun. The solar system had acquired a new rhythm. A planet farther from the Sun generally takes longer to complete its orbit. The wandering lights were no longer moving through arbitrary combinations of circles. Their paths followed elegant mathematical relationships centered upon the Sun, yet nobody knew what force made them do this. Kepler could describe the dance without fully explaining the music. There is also scholarly uncertainty surrounding how particular intellectual influences shaped his developing physical ideas. Historians continue examining the complicated mixture of mathematics, philosophy, observation, theology, and earlier astronomical traditions within his work. Scientific reasoning does not arrive separated neatly into modern categories. Kepler's universe was mathematical, physical, and deeply meaningful to him. You now stand beneath a transformed sky. Earth moves. Mars follows an ellipse. The planets change speed as they orbit. The Sun has become the organizing center of planetary motion. But these conclusions still depend largely upon naked-eye observations and mathematical argument. Then, almost immediately, a new instrument arrives. It is modest at first, a tube, two pieces of glass, a narrow field of view. Point it toward Earth, and distant objects appear closer. Point it toward the heavens, and the ancient lights stop being merely lights. The Moon becomes a landscape. Jupiter becomes a miniature system. Venus reveals a secret geometry. Humanity has spent thousands of years measuring points in the sky. Now, for the first time, those points are about to become places. In the winter of 1609, you can imagine standing beside Galileo Galilei as he carries a narrow telescope into the cold Italian night. The instrument looks surprisingly modest. It is little more than a tube containing carefully shaped pieces of glass, yet it extends human sight farther than any naked eye can reach. Your fingers feel the chill of the tube. Wood smoke drifts between nearby buildings, while distant footsteps echo through streets, gradually becoming quiet. Galileo raises the instrument toward the Moon. The familiar silver disk changes. Its boundary between light and darkness is rough rather than perfectly smooth. Bright peaks catch sunlight, while nearby regions remain dark. Shadows stretch across the surface. Galileo interprets these patterns as mountains, valleys, and uneven terrain. The Moon resembles a world. This matters because influential traditions had treated celestial bodies as fundamentally different from imperfect Earth. Now the nearest heavenly object appears physically rugged. The heavens are becoming less perfect and more interesting. Galileo was not the first person to build a telescope, nor was he necessarily the first to point one toward the sky. The instrument emerged from developments in European lens-making, particularly in the Netherlands. Historians still examine competing claims concerning exactly who deserves priority for its invention. Galileo's achievement was to improve the instrument and exploit it systematically for astronomy. Then he pointed it toward Jupiter. During January 1610, Galileo noticed small points of light near the planet. Their positions changed from night to night. At first, they could resemble ordinary stars. Repeated observation revealed something extraordinary. They were orbiting Jupiter. Today, you know them as Io, Europa, Ganymede, and Callisto, the four largest moons of Jupiter. To Galileo, their existence provided a powerful lesson. Not everything revolves around Earth. You return night after night. Jupiter remains bright in the telescope, while its tiny companions rearrange themselves around it. One appears on one side, another disappears. Later, it returns. The movements form a miniature celestial system. Earth is no longer the only possible center of orbital motion. This observation does not by itself prove that Earth circles the Sun. Tycho's hybrid system can also accommodate moons orbiting Jupiter, but the simple claim that every celestial object must circle Earth has become impossible to maintain. Then Venus reveals something even more damaging to the traditional Ptolemaic arrangement. Through a telescope, Venus displays phases. Sometimes more of its illuminated hemisphere faces Earth. At other times, Venus appears as a crescent. Its apparent size also changes. The full range of observed phases fits naturally if Venus orbits the Sun. The old Ptolemaic configuration cannot reproduce the complete pattern. A major piece of celestial geometry has become visible. Yet heliocentrism is still not instantly victorious. The Tychonic model also places Venus around the Sun, while keeping Earth stationary. The debate therefore continues. Scientific revolutions are inconveniently reluctant to finish in a single dramatic evening. Galileo observes still more. The sun itself appears marked by dark spots. Watching sunspots change and move suggests that the sun rotates. Again, the supposedly flawless heavens reveal variation. Looking towards Saturn creates a stranger problem. Galileo's telescope cannot resolve the planet's rings properly. Instead, Saturn seems accompanied by unusual extensions or companion-like shapes. Later observations become even more confusing as the rings change orientation from Earth's viewpoint. At times, the strange appendages nearly disappear. Galileo does not know what he is seeing. The solar system has offered him a puzzle. His instrument is just barely powerful enough to reveal. Decades later, Christian Huygens will interpret Saturn as a planet surrounded by a thin, flat ring. In 1655, Huygens also discovers Titan, Saturn's largest moon. The outer planets are beginning to acquire families. Then Giovanni Domenico Cassini identifies additional Saturnian moons and notices a dark division within the rings. Every improvement in telescopes seems to multiply the solar system. Even the moon refuses to remain simple. Telescopic observers begin mapping its visible features and giving names to mountains, craters, and dark plains. Those dark regions are eventually called seas because early observers wondered whether they might contain water. They do not. The name survives anyway. Astronomy is full of linguistic fossils from reasonable mistakes. Mars also becomes more than a reddish point. Although early telescopes reveal frustratingly little detail, observers sometimes report changing markings. As instruments improve, astronomers attempt to determine the planet's rotation. Jupiter displays bands and changing atmospheric features. The giant planet becomes visibly dynamic. Its famous Great Red Spot, or features related to it, enters the historical observational record during the 17th century. Though identifying the earliest observations precisely remains debated. The farther humanity looks, the less static the heavens become. There is another transformation underway. Telescopes begin improving rapidly. Longer focal lengths and better lenses reduce some optical problems, although early refracting telescopes can become astonishingly awkward. Some instruments grow many meters long. Observers struggle with narrow fields of view, vibration, weather, and imperfect glass. The romantic image of astronomy sometimes forgets how much time astronomers spend fighting equipment. You might spend a cold evening adjusting a telescope only for clouds to arrive. The universe has always had excellent timing. Despite these difficulties, measurements improve. In 1676, observations of Jupiter's moon Io help Ola Roma investigate an astonishing question. Does light travel instantaneously? The timing of Io's eclipses appears to shift depending upon Earth's changing distance from Jupiter. Roma interprets the variation as evidence that light requires time to cross space. Light has a finite speed. This means every astronomical observation becomes a view into the past. When you see the moon, you see it slightly more than 1 second earlier. Sunlight reaching your face is already about 8 minutes old. Light from Saturn has traveled much longer. The telescope has therefore revealed not only distant places, it has quietly revealed distant times. Meanwhile, Johannes Kepler's mathematical laws remain unexplained at the deepest physical level. Why should planets follow ellipses? Why should their speeds change predictably? Why should orbital periods follow a mathematical relationship with distance? The answers require a new understanding of motion. Galileo contributes important ideas about falling bodies and inertia. Other natural philosophers investigate forces, trajectories, and celestial motion. The old division between earthly physics and heavenly physics begins collapsing. A cannonball and a moon might belong to the same science. That possibility is revolutionary. You can feel the conceptual pieces moving closer together. Kepler has supplied mathematical laws for planetary motion. Galileo has strengthened the study of motion, while telescopic astronomy reveals physical worlds. Roma has shown that even light crosses the solar system in measurable time. Yet the mechanism holding planets in orbit remains missing. Some thinkers imagine vortices carrying worlds through a subtle cosmic medium. Others search for forces acting across space. Arguments multiply. One particularly consequential argument involves Robert Hooke and Isaac Newton, whose exchanges later become part of complicated disputes over priority and influence. Historians continue examining exactly how different contributions shaped Newton's eventual formulation of gravitation. Great ideas rarely emerge from intellectual emptiness. Newton inherits a century crowded with observations, mathematics, disagreements, and unfinished problems. Soon he will connect them. For now, you lower the telescope. The eyepiece leaves a faint circle around your vision. Cold night air touches your face. Above you, Jupiter appears once again as an ordinary bright point. Your naked eye cannot see its moons. Saturn looks calm and singular despite its enormous rings. Venus gives no obvious hint of its phases. The telescope has created a peculiar new reality. There is the solar system humans see naturally. Then there is the solar system revealed by instruments. From this moment onward, those two versions will separate increasingly. Larger telescopes will reveal fainter moons. Spectroscopes will uncover chemical compositions. Cameras will preserve light too faint for the eye. Radio antennas will listen to invisible wavelengths. Spacecraft will eventually carry instruments directly to the planets. But before humanity can travel through the solar system, it must understand what keeps the system together. The answer begins with a familiar sensation. You release an object. It falls. The moon does not fall onto Earth. Earth does not fall into the sun. Or perhaps, in a much stranger sense, they are falling all the time. You move into the later 17th century, carrying a question that now seems almost embarrassingly simple. Why do planets remain in orbit? Kepler has described their motions with extraordinary precision, but mathematical patterns alone do not explain what physically guides the worlds. Galileo has transformed the study of motion. Telescopes have shown moons circling Jupiter and revealed that celestial bodies are physical places rather than perfect lights. The pieces are waiting to be connected. You find Isaac Newton working in an England filled with scientific argument, mathematical innovation, political upheaval, and the lingering memory of devastating disease. Imagine a quiet room after sunset. A fire gives off a dry smell of burning wood. Paper scratches beneath a pen, while rain taps irregularly against a window. Outside, the moon follows the same path humans have watched since prehistory. Newton asks whether its motion might obey the same rules as objects falling near Earth's surface. The famous story says that an apple helped inspire his thoughts about gravity. An apple probably did play some role in Newton's later recollections, although the polished tale of a fruit dramatically striking his head belongs more comfortably to legend. Reality is less theatrical. This is fortunate for Newton. The important idea is that falling apples and orbiting moons need not belong to separate categories of nature. Imagine throwing a stone horizontally. Gravity pulls it downward until it strikes the ground. Throw it faster, and it travels farther before landing. Now imagine an impossibly powerful launch from high above Earth's atmosphere. The object falls toward Earth, but Earth's curved surface drops away beneath it at the same rate. It keeps missing the ground. That is an orbit. The moon is falling. Earth is falling around the sun. Every planet is continually falling while moving sideways fast enough to avoid the object attracting it. The solar system becomes a magnificent arrangement of controlled misses. Newton develops this insight into a theory of universal gravitation. Every mass attracts every other mass. The gravitational force becomes stronger with greater masses and weaker as the distance between them increases. More specifically, the attraction falls according to the square of the distance, double the separation, and the gravitational attraction becomes 1/4 as strong. This simple relationship reaches across the solar system. The same underlying physics can describe an apple falling near Earth. the Moon circling Earth, and Jupiter traveling around the Sun. The ancient division between earthly and celestial physics collapses. There is one nature. Newton publishes his great mathematical work on motion and gravitation in 1687. Within it, his laws of motion provide a framework for understanding how forces change movement. Inertia explains why an object continues moving unless a force changes that motion. Gravity continually bends planetary trajectories. Kepler's elliptical orbits can now emerge from deeper physical principles. The planetary dance finally has something resembling its music. Yet Newton himself is uneasy about one feature of gravity. How does one object influence another across apparently empty space? His mathematics describes the attraction with extraordinary success, but the underlying mechanism remains mysterious. Later physics will transform the interpretation of gravity again. For now, its predictive power is remarkable. You can begin weighing worlds without visiting them. If a moon circles a planet, its orbital motion contains information about the planet's mass. Observe how quickly the moon travels and how far away it orbits. Then use gravitational mathematics. The invisible pull becomes measurable. Jupiter's 4 large moons therefore become more than discoveries. They become scales. Saturn's moons serve a similar purpose. Astronomers can compare the gravitational influence of distant planets, even though no human will approach them for centuries. The solar system is becoming a laboratory. Comets provide another dramatic test. For much of history, comets have seemed unpredictable visitors. Their bright heads and long tails appear suddenly, sometimes inspiring fear or fascination before fading away. Newtonian gravity suggests that at least some comets may follow enormous orbits around the Sun. Edmund Halley investigates this possibility. He studies observations of comets seen in different years and concludes that appearances in 1531, 1607, and 1682 likely belong to the same returning object. He predicts that it will return around 1758. Halley does not live to see the result. The comet does. Its successful return provides a powerful demonstration that Newtonian mechanics can predict motion across decades. The heavens have become calculable in a new way. A comet is no longer merely an omen arriving from unknown regions. It can be a member of the solar system following a long gravitational path. There is a wonderfully human detail hidden inside such calculations. Predicting a comet accurately is difficult because the Sun is not the only object pulling upon it. Jupiter and Saturn also disturb its motion. The solar system is not a collection of isolated two-body problems. Everything tugs on everything else. Usually the effects are small. Over enough time, small effects accumulate. Mathematicians spend the 18th century developing increasingly sophisticated methods for handling these gravitational interactions. Their calculations reveal that planets perturb one another. Jupiter shifts Saturn slightly. Saturn responds. Earth feels smaller influences from neighboring worlds. The solar system becomes less like a perfect clock and more like an enormous gravitational conversation. Scholars would later investigate whether this conversation remains stable over immense spans of time. Even Newton worried about long-term planetary behavior. Subsequent mathematicians, including Laplace and Lagrange, developed powerful techniques for celestial mechanics. Some apparent irregularities could be explained as periodic gravitational interactions rather than evidence that the system required occasional correction. Yet complete stability proved more complicated than early mathematical optimism suggested. Modern studies reveal chaotic features in planetary dynamics across very long timescales. Small uncertainties can eventually grow. The planets are predictable with astonishing accuracy over human timescales. But eternity is another matter. There is something gently unsettling about that. Even the clockwork solar system is not perfectly clock-like. Another mystery concerns its beginning. Newtonian mechanics explains how planets move once they exist. It does not automatically explain why the planets occupy roughly the same plane or travel around the Sun, mostly in the same direction. Those patterns look like clues. Perhaps the solar system has a shared origin. During the 18th century, thinkers begin proposing that the sun and planets formed naturally from rotating material. Immanuel Kant suggests that gravitational processes within a primordial cloud could contribute to the formation of celestial systems. Pierre-Simon Laplace later develops an influential nebula hypothesis involving a rotating, contracting mass. These early ideas are not modern planetary formation theory. Important details will change dramatically. Still, they introduce a powerful possibility. The solar system has a history. The planets were not necessarily placed into their present orbits fully formed. They might have emerged through physical processes from common material. Astronomers cannot yet test this idea directly. They know little about planetary chemistry. They have no photographs of other forming star systems. They cannot analyze primitive meteorites with laboratory instruments. The age of the Sun is unknown. Even Earth's age remains fiercely uncertain. Historians of science continue examining how theological, philosophical, geological, and physical ideas interacted within these early theories of cosmic origins. There was no single clean transition from an eternal arrangement to an evolutionary universe. The change occurred gradually. Meanwhile, telescopes continue improving. Reflecting telescopes use mirrors rather than relying entirely upon lenses. Newton himself constructs an influential reflecting design. Larger instruments collect more light. Fainter objects become visible. The boundaries of the known solar system begin to feel less secure. For thousands of years, Saturn has marked the outermost known planet. Beyond Saturn lies darkness populated by distant stars and occasional comets. Nobody suspects that another major planet is waiting there within reach of a telescope. It has probably been seen before. Observers may even have recorded it. They simply mistook it for a star. That distinction captures how discovery often works. Something can sit directly inside your observations without revealing what it is. You only need to notice that it moves. Soon, an astronomer named William Herschel will do exactly that. Saturn will lose its ancient position at the frontier. The solar system will suddenly become twice as wide. And for the first time in recorded history, humanity will discover a planet that the unaided human eye had never clearly recognized as a wandering world. In March 1781, you stand beneath the cold evening sky of Bath, England, beside a musician who has become obsessed with astronomy. His name is William Herschel. The telescope before him is a reflecting instrument he has built and polished with extraordinary patience. The night smells faintly of damp earth and chimney smoke. Your fingers stiffen in the cold, while Herschel methodically examines one small region of sky after another. He is not searching for a new planet. Nobody expects one. For all of recorded history, Saturn has marked the distant boundary of the known planetary family. Mercury, Venus, Mars, Jupiter, and Saturn have been visible to human eyes since antiquity. Then Herschel notices something unusual. The object looks different from an ordinary star. When greater magnification is applied, stars remain essentially points, but this object shows a tiny disk. At first, Herschel suspects that he has found a comet. Continued observations reveal something stranger. The object follows an orbit beyond Saturn. Humanity has discovered Uranus. The known solar system suddenly expands. Uranus takes about 84 Earth years to circle the Sun, traveling at an average distance roughly 19 times Earth's distance from our star. Sunlight there is weak. From Uranus, the Sun would still appear brilliant, but far smaller than it does from Earth. The discovery changes astronomy psychologically as much as geographically. Saturn was not an edge. If one unknown planet had been hiding beyond it, perhaps others were waiting farther away. There is also a delightful historical irony. Uranus had been observed before Herschel. Earlier astronomers recorded it as though it were an ordinary star because its slow movement was not recognized. The planet had quietly entered human records without receiving an introduction. Herschel also wanted to name his discovery after King George III. Other naming proposals circulated before Uranus eventually became standard. Even planets must sometimes survive administrative discussions. Telescopes soon reveal moons around the New World. Herschel discovers Titania and Oberon in 1787. Later observers add Ariel, Umbriel, and eventually many smaller satellites. Uranus also possesses rings, although those will remain unknown until the 20th century. The outer solar system is becoming increasingly populated. Then another puzzle appears much closer to the Sun. Astronomers have noticed a curious gap between Mars and Jupiter. A mathematical pattern concerning planetary distances encourages some observers to suspect that a missing world might occupy this region. The pattern itself is not a fundamental law of planetary formation, despite the excitement it generated. Still, it helps motivate organized searches. On the first day of 1801, Giuseppe Piazzi observes a small moving object while working in Palermo. He initially thinks it might be a comet. Its orbit lies between Mars and Jupiter. The object becomes known as Ceres. For a moment, the missing planet appears to have been found. Then more objects appear. Pallas is discovered in 1802. Juno follows in 1804. Vesta appears in 1807. The supposedly empty region contains a population. During the 19th century, discoveries multiply until astronomers increasingly classify these small bodies separately. They become asteroids. The solar system is no longer simply a sequence of large planets separated by empty space. Between Mars and Jupiter lies an enormous belt of smaller objects. Most are irregular fragments, rather than miniature spherical worlds. Ceres is large enough for its own gravity to pull it into a rounded shape, making it unusual among its neighbors. Modern astronomy classifies it as a dwarf planet. These bodies will eventually become precious clues to the solar system's formation. For now, they are mostly mysterious points of light. Meanwhile, Uranus refuses to move exactly as expected. Astronomers calculate its orbit using Newtonian gravity and account for known planetary influences. Small discrepancies remain. Perhaps the observations are wrong. Perhaps the calculations need improvement. Or perhaps another unseen planet is pulling upon Uranus. This possibility is extraordinary. Instead of finding a world first and calculating its orbit afterward, mathematicians attempt the reverse. They use gravitational disturbances to predict where an invisible planet should be. Urbain Le Verrier in France and John Couch Adams in Britain independently work on the problem. Their calculations are not identical, and the history of priority becomes complicated. Historians continue debating aspects of the relative contributions, communications, and later national claims surrounding the discovery. Astronomy can be calm. Astronomers are not always so obliging. In September 1846, Johann Gottfried Galle and Heinrich d'Arrest search near the position indicated by Le Verrier's calculations. They find a star-like object absent from their comparison chart. Its movement confirms the discovery. Neptune has entered the known solar system. The achievement feels almost magical. A planet has been found through mathematics. Newton's invisible gravitational attraction has pointed toward an unseen world billions of kilometers away. Neptune orbits roughly 30 times farther from the Sun than Earth does. One journey around the Sun requires about 165 Earth years. Since its discovery, Neptune has completed only a little more than one full orbit. Its existence pushes the planetary frontier outward again. Telescopes also reveal that Neptune has a moon. William Lassell discovers Triton only weeks after the planet itself is identified. Triton behaves strangely. It travels around Neptune in the direction opposite the planet's rotation. Modern scientists interpret this retrograde orbit as strong evidence that Triton was probably captured rather than forming normally beside Neptune. That conclusion lies far in the future. 19th-century observers simply discover another peculiar member of an increasingly peculiar system. The century also transforms what astronomers can learn from light. For thousands of years, astronomy has primarily measured position, brightness, and motion. Now spectroscopy begins opening another dimension. When light is separated into its component colors, dark or bright lines appear at particular wavelengths. Those lines contain information about matter. Laboratory experiments reveal that different chemical elements produce characteristic spectral signatures. Suddenly, astronomers can begin investigating what distant objects are made from. The heavens are no longer beyond chemistry. The sun becomes especially important. Its spectrum contains numerous dark absorption lines. Researchers connect these features with substances familiar on Earth. The same elements exist in the sun. The ancient boundary between celestial and terrestrial matter weakens again. One particularly charming example involves helium. Evidence for the element appears in the solar spectrum before helium is identified on Earth. A substance is effectively recognized in the sun before humans isolate it from their own planet. The sky has become a laboratory again. Photography also enters astronomy. A photographic plate can accumulate light over time and preserve observations independently of the observer's memory. Objects too faint for comfortable visual study can leave measurable traces during long exposures. Astronomy begins moving beyond the limitations of the human eye. This technological transformation reaches farther than the solar system. Nebulae, star clusters, and the structure of the Milky Way attract increasing attention. William Herschel had already attempted to map the stellar system by counting stars in different directions. His model was limited by interstellar dust and incomplete knowledge of stellar distances. Still, the sun was becoming less cosmically central. First, Earth lost the center of planetary motion. Now the sun itself seems to inhabit a much larger stellar universe. That expanding perspective changes how astronomers think about planetary origins. If the sun is one star among enormous numbers of stars, perhaps planetary systems need not be unique. Nobody yet knows. No confirmed exoplanet has been detected. The question remains almost entirely beyond observational reach. Closer to home, another mystery develops around Neptune. Calculations and observations encourage speculation that additional bodies might exist beyond the known planet. Some apparent discrepancies will later prove misleading because Neptune's mass was not yet known accurately enough. Nevertheless, searches continue. The solar system has developed a habit of placing new frontiers behind old ones. You step outside beneath a 19th century night. Uranus is invisible to most casual eyes. Neptune is hopeless without optical assistance. Thousands of asteroids move silently between Mars and Jupiter. Comets travel along enormous paths. The sun contains elements recognizable through lines of light. Humanity has progressed from identifying wanderers to discovering worlds mathematically. Yet the deepest question remains unanswered. Why does the solar system possess this particular arrangement? Why are rocky planets concentrated near the sun? Why do giant planets dominate farther away? Why are asteroids scattered between Mars and Jupiter? Why do most planets orbit in nearly the same plane and direction? Those patterns suggest a shared beginning. The old nebular ideas now need physical evidence. That evidence will come from geology, physics, chemistry, meteorites, and eventually observations of young stars. The solar system is about to stop being merely a collection of moving worlds. It is about to acquire an age. And once you know its age, you can begin asking what happened at the beginning. You enter the 20th century carrying a question that earlier astronomers could describe but never answer securely. How old is the solar system? The planets clearly share patterns suggesting a common origin. Most orbit the sun in the same direction. Their paths lie near a common plane. Small bodies occupy distinctive populations, while rocky planets dominate the inner regions and giant planets occupy greater distances. The arrangement looks inherited. But inherited from what? To find the answer, you must briefly leave the telescope and enter a laboratory. Imagine a quiet room filled with glassware, metal instruments, paper notes, and the faint, chemical smell of early experimental science. On a table rests an unimpressive piece of rock. It does not glow. It does not move. Yet material like this will eventually reveal when the solar system began. During the 19th century, geologists had already discovered that Earth must be far older than traditional short chronologies suggested. Layers of rock recorded immense sequences of change. Fossils revealed vanished ecosystems. Erosion and sedimentation demanded enormous spans of time. Charles Darwin's theory of evolution also required a deep history for life. Physics, however, initially created difficulties. Lord Kelvin attempted to estimate Earth's age by treating the planet as a body cooling from an initially hot condition. His calculations suggested ages far below modern values. Kelvin did not know about radioactive heating within Earth. An invisible source of energy was missing from the model. Then radioactivity was discovered. Atoms were not necessarily permanent, unchanging units. Certain unstable isotopes transformed into other isotopes at measurable rates. This provided nature with something astonishingly useful: a clock. If you know how rapidly a radioactive isotope decays, and you can measure parent and daughter isotopes within a suitable mineral, you can estimate when that material formed. Geological time becomes numerical. During the 20th century, radiometric dating methods improved steadily. Scientists date ancient terrestrial minerals. Then they turn toward meteorites. Meteorites are especially valuable because Earth's surface is geologically restless. Crust is melted, buried, altered, eroded, and recycled. Many meteorites, however, preserve material dating from the solar system's earliest history. They are fragments of ancient construction debris. In the 1950s, geochemist Claire Patterson uses lead isotope measurements from meteorites to estimate an age of roughly 4.55 billion years for Earth and the solar system. Modern measurements refine the picture. The solar system formed about 4.6 billion years ago. You can finally place a date near the beginning. Now travel backward. The planets disappear. Earth vanishes beneath you. Mars, Jupiter, Saturn, Uranus, and Neptune dissolve from familiar worlds into ingredients that have not yet assembled. Even the young sun is still forming. You enter a region of the Milky Way containing cold gas and microscopic dust. There is no clean boundary like the edge of a cloud in Earth's atmosphere. Instead, material spreads across an enormous volume of space. Much of it consists of hydrogen and helium. Heavier elements are present in smaller quantities. Those heavier ingredients carry an older history. Carbon, oxygen, silicon, iron, and many other elements were produced through earlier generations of stars and stellar explosions. The solar system is therefore built from recycled cosmic material. Your body will eventually be built from it too. Something causes part of this interstellar material to collapse gravitationally. The exact trigger remains uncertain. A nearby stellar explosion may have contributed, or internal processes within a molecular cloud may have been sufficient. Researchers continue investigating isotopic evidence and models of the Sun's likely birth environment. The broad sequence is clearer than the precise opening event. Gravity pulls material inward. As the cloud contracts, small initial rotation becomes increasingly important. You can picture a spinning figure, drawing their arms inward and rotating faster. The analogy is imperfect, but the principle of angular momentum helps explain why collapsing material develops stronger rotation. The cloud flattens. A disk forms around a growing central concentration. This is the protoplanetary disk. At its center, pressure and temperature rise as material continues falling inward. Eventually, conditions become extreme enough for sustained hydrogen fusion to begin. The young sun becomes a star. Around it remains a rotating disk of gas, dust, ice, and increasingly complicated solids. The solar system is being assembled. This basic picture descends intellectually from old nebular ideas, but modern astronomy adds evidence earlier thinkers could never possess. Telescopes can observe young stars surrounded by disks. Infrared and radio observations penetrate dusty stellar nurseries. Modern observatories even resolve structures within some protoplanetary disks. Dark gaps and rings suggest that planet formation may already be reorganizing material. Humanity can now watch other planetary systems being born. The chemistry within our own disk depends strongly upon temperature. Near the young sun, conditions are hot. Many volatile substances cannot condense easily into solid grains. More heat-resistant materials, including metals and silicate minerals, survive. Farther outward, temperatures fall. Water and other compounds can freeze into ices. This temperature difference helps shape the contrasting families of planets. The inner solar system has relatively limited solid material available. Small rocky worlds begin there, farther from the sun, especially beyond regions where abundant volatile compounds can freeze. Much more solid material becomes available for building planetary cores. Some growing bodies become massive enough to capture enormous envelopes of hydrogen and helium before the disk gas disappears. The giant planets emerge, yet the process begins with dust. Tiny particles collide. Some stick through electromagnetic forces. Larger aggregates form. Eventually, growth reaches objects whose gravity becomes important. These planetesimals collide, merge, scatter, and sometimes shatter. Planetary construction is not gentle. Imagine standing somewhere inside this disk, although standing would be impossible. The young sun glows nearby. Dust fills the environment. Countless solid bodies follow intersecting paths. Collisions occur across scales ranging from microscopic grains to growing planetary embryos. The solar system is less like a peaceful clockwork and more like a construction site without a supervisor. The oldest known solid materials preserved in primitive meteorites provide particularly important evidence. Calcium-aluminum-rich inclusions formed extremely early, around 4.567 billion years ago. Their ages provide one of the best markers for the beginning of solar system history. Meteorites also contain chondrules, small, once-molten droplets whose origins remain subjects of active research. Scientists debate the precise heating mechanisms that produced many chondrules. Shock waves, collisions, magnetic processes, and other mechanisms have been proposed. A tiny sphere inside a meteorite can preserve an argument lasting decades. These primitive materials tell you that the early solar system changed rapidly. Within a few million years, dust had become organized into increasingly large bodies. Some planetesimals grew hot enough to melt internally. Dense metals sank toward their centers, while lighter rocky materials rose above. Differentiated miniature worlds appeared. Then many were destroyed by collisions. Fragments of their metallic cores survive today as iron meteorites. Fragments of their rocky mantles and crusts also reach Earth. When you hold certain meteorites, you may therefore be holding pieces of worlds that disappeared billions of years before humans existed. The chemical evidence also helps connect the planets to a common source. Isotopic patterns divide meteorites into populations that appear to have formed in different regions of the young disk. Scientists increasingly use these differences to reconstruct how material moved and how rapidly planets grew. Jupiter may have become massive surprisingly early. If so, its gravity could have separated reservoirs of material and profoundly influenced the developing solar system. Exactly how and where the giant planets formed remains uncertain. Their present locations may not be their birthplaces. That realization will become important. The neat textbook picture of planets forming quietly where you find them today has given way to something more dynamic. Planets migrate. Growing worlds scatter smaller bodies. Resonances shift. Entire populations can be rearranged. The solar system has a childhood, but it was not a calm childhood. You look around this ancient disk once more. There is no blue Earth. There is no familiar moon. Mars is not yet the small red desert you recognize. Jupiter may still be gathering its enormous atmosphere. Asteroids have not yet settled into their modern belt. Everything familiar exists only as possibility. Yet the ingredients are here. Iron destined for planetary cores moves among dust grains. Water that may eventually reach young worlds freezes in colder regions. Carbon compounds drift through the disk. The future planets are assembling from the remains of older stars. For the first time in our journey, human discovery has carried you far enough backward to watch the physical solar system begin. Now the cloud has become a disk. The disk has become countless solid bodies, and those bodies are about to collide until only a handful of major worlds remain. You remain inside the young solar system, roughly 4.6 billion years ago, while the orderly arrangement you know today is still unfinished. The newborn sun dominates the center. Around it, the protoplanetary disk has begun thinning, but countless solid bodies continue traveling through overlapping paths. There are no quiet planetary neighborhoods yet. There is traffic. Dust grains have become pebbles, larger aggregates, planetesimals, and eventually objects hundreds or thousands of kilometers across. Gravity increasingly controls what happens next. A growing body attracts nearby material. Every successful collision increases its mass, strengthening its ability to collect still more material. Growth can accelerate. Planetary embryos emerge in the inner solar system. Several such embryos may eventually reach sizes comparable with the Moon or Mars. They share space with vast populations of smaller objects. Collisions are unavoidable. You cannot hear them. Space carries no ordinary sound between these bodies, despite what generations of dramatic films might politely suggest. Instead, there is silence. A collision between planetary embryos can release unimaginable energy without producing a single audible boom for a distant observer. Rock melts. Material vaporizes. Fragments spread across new orbits. Then gravity begins gathering some of them again. The 4 rocky planets emerge from this extended violence. Mercury forms closest to the Sun. Venus grows into a world almost Earth's size. Earth assembles slightly farther outward. Mars remains much smaller. Why Mars stopped growing so early remains an important question. One possibility involves Jupiter. If the giant planet formed early and moved through part of the young solar system, its gravity may have disturbed material that otherwise could have contributed to Mars. Models known as the Grand Tack explore a dramatic possibility in which Jupiter migrated inward before reversing direction after interacting with Saturn. Such movement could help explain several features of the inner solar system. It remains a model rather than a confirmed historical recording. Researchers continue testing whether this scenario best explains the evidence. Planetary formation is frustrating that way. You arrive billions of years after the event and discover that nobody preserved security footage. Mercury presents another puzzle. It possesses an unusually large metallic core compared with its overall size. Perhaps a giant collision stripped away much of an early rocky mantle. Perhaps conditions within the inner disk naturally produced a metal-rich planet. Other explanations remain possible. Modern measurements continue narrowing the options. Venus and Earth initially appear more closely related. They have similar sizes and comparable bulk compositions, yet their later histories will diverge dramatically. For now, both are young rocky worlds experiencing impacts, volcanism, internal differentiation, and changing atmospheres. Farther outward, the construction process follows different rules. Beyond the warmer inner disk, ices provide additional solid material. Planetary cores can grow larger. Jupiter becomes the dominant world. Its core and surrounding material acquire enough gravity to capture vast quantities of hydrogen and helium before the gaseous disk disappears. The result is enormous. Jupiter eventually contains more mass than all the other planets combined. Its formation influences nearly everything around it. Saturn grows into another gas giant. It remains much less massive than Jupiter, but still dominates its region. Farther outward, Uranus and Neptune develop differently. They contain greater proportions of heavier substances compared with Jupiter and Saturn, and capture smaller hydrogen-helium envelopes. Modern astronomers call them ice giants. Their exact formation remains difficult to explain at their present distances because the outer disk may have contained too little material for rapid growth there. This suggests that they may have formed closer to the Sun before migrating outward. Again, the solar system refuses to stay where you put it. Planetary migration has become one of the most important ideas in modern theories of planetary evolution. A young planet exchanges gravitational energy and angular momentum with surrounding gas or smaller bodies. Its orbit can change. Several planets interacting with one another can rearrange the system dramatically. Modern exoplanet discoveries strengthen this lesson. Astronomers have found giant planets extremely close to other stars, showing that planetary systems can experience substantial migration. Our own arrangement suddenly looks less inevitable. Jupiter and Saturn may once have occupied different orbits. Uranus and Neptune may have shifted dramatically. Some simulations even explore whether the early solar system contained an additional giant planet that was later ejected. There is no direct proof that such a lost planet existed. Still, models with an extra giant can sometimes reproduce aspects of the surviving system. Imagine an entire planet being thrown into interstellar darkness. The possibility sounds extravagant. Gravity is perfectly capable of extravagance. Meanwhile, smaller bodies suffer the consequences of giant planetary rearrangement. Some are thrown inward, others are scattered outward. Many are ejected from the solar system entirely. Populations of asteroids and icy bodies are mixed, depleted, and redistributed. The modern asteroid belt is therefore not simply a failed planet waiting patiently between Mars and Jupiter. Jupiter's gravitational influence prevented much of that region's material from assembling into a major world. Collisions then continued grinding and reshaping the survivors. Ceres grew large enough to become rounded. Vesta partially differentiated and preserved an ancient crust. Other asteroids became irregular fragments. Some travel in orbital resonances with Jupiter. Others share the giant planet's orbit near gravitationally stable regions and are known as Trojan asteroids. Even these populations preserve clues to ancient migration. Far beyond the giant planets, icy planetesimals remain. Some eventually occupy the Kuiper belt beyond Neptune. Others are scattered onto highly elongated orbits. Still more may populate an enormous distant reservoir surrounding the solar system, called the Oort cloud. The Oort cloud has never been observed directly as a resolved structure. Its existence is inferred largely from the orbits of long-period comets. How it formed, how massive it is, and precisely where its boundaries lie remain uncertain. The solar system becomes hazier at its edges. Closer to the Sun, the era of giant impacts continues. Planetary embryos collide until only a small number of large terrestrial worlds remain. Earth experiences the most consequential collision in its history. A body, often called Theia, perhaps roughly comparable to Mars in size, strikes the young Earth. The impact ejects enormous quantities of material. Some of that debris remains gravitationally bound around Earth. A disk forms. Material in that disk gathers. The Moon emerges. This giant impact model explains many important features of the Earth-Moon system, but its details continue evolving. Measurements of lunar samples reveal strong chemical and isotopic similarities between Earth and Moon. That creates constraints on exactly how the impact occurred and how thoroughly material mixed afterward. Researchers still debate the impactor's size, speed, angle, composition, and the precise sequence of lunar assembly. The broad picture is compelling. The fine details remain alive. Afterward, the Moon orbits much closer to Earth than it does today. Tidal interactions gradually transfer angular momentum. Earth's rotation slows, while the Moon moves outward. The length of an Earth day changes across geological time. Even today, laser measurements show the Moon receding by several centimeters each year. A primordial collision is still quietly affecting the distance between Earth and its companion. Other worlds acquire moons through different pathways. Some satellites form within disks around giant planets. Others are probably captured objects. Triton's backward orbit around Neptune strongly suggests capture. Mars obtains two tiny irregular moons, Phobos and Deimos, whose exact origins remain debated. They might be captured asteroid-like bodies, products of a giant impact, or descendants of debris that reorganized around Mars. Saturn eventually possesses an extraordinary system of moons and rings. Jupiter collects dozens of satellites across different orbital families. The solar system becomes a hierarchy. Moons circle planets. Planets circle the sun. Small bodies occupy resonances, belts, clouds, and wandering paths between them. Yet construction has not completely ended. Impacts continue. For a long time, scientists discussed a distinct episode of intense bombardment around 3.9 billion years ago, sometimes called the Late Heavy Bombardment. Modern interpretations are more cautious. Lunar impact ages and dynamical evidence may reflect a more complicated decline or restructuring rather than one sudden universal spike. The precise history remains debated. What is certain is that young planetary surfaces endured far more frequent large impacts than they do today. The craters covering the Moon preserve that violent memory. Earth once received similar scars. Weather, oceans, volcanism, erosion, and plate tectonics erased most of them. You now drift above the inner solar system after much of the chaos has weakened. Mercury survives close to the Sun. Venus occupies the next orbit. Earth travels with its newly formed moon. Small Mars circles beyond. The asteroid belt lies scattered before massive Jupiter. Saturn follows. Uranus and Neptune occupy the distant cold. The architecture is becoming recognizable. But familiar orbits do not mean familiar worlds. Earth is not yet the blue planet beneath your feet. Its atmosphere, oceans, crust, and climate will undergo immense changes. Venus may not yet resemble the furnace it becomes. Mars may possess rivers and lakes. Moons around the giant planets hide their own evolving histories. The solar system has finished much of its construction. Now comes transformation. Among all these worlds, one small rocky planet will develop oceans that persist, chemistry that becomes increasingly complicated, and eventually something capable of looking back toward the planets. Earth is about to become unusual. You now approach the young Earth after the great collisions of planetary construction have begun to fade. It is recognizable mainly by its orbit. The surface would feel completely alien. Heat escapes from the planet's interior while impacts continue delivering additional energy. Volcanic gases enter a changing atmosphere, and molten regions slowly cool into solid crust. The air would be impossible for you to breathe. There are no forests, birds, insects, or grasses. There is not even the familiar smell of soil, because soil, as you know it, does not yet exist. Above this restless landscape hangs a young moon. It is much closer than the moon you see today, and therefore appears dramatically larger in the sky. Earth also rotates faster. Tidal interactions between Earth and Moon will gradually slow that rotation while pushing the Moon outward. The planet is already changing, simply because its companion exists. Water soon becomes one of the central questions. Where did Earth's oceans come from? Some water was probably incorporated into the material from which Earth formed. Additional water-bearing material may have arrived through asteroids and other small bodies. Comets were once popular candidates for delivering much of the oceans, but measurements show that the story is more complicated. Different solar system bodies contain different isotopic signatures. Scientists compare ratios involving hydrogen to determine which sources most closely resemble terrestrial water. Evidence currently favors substantial contributions from water-rich rocky material, although the exact mixture remains uncertain. The oceans probably have more than one source. As Earth cools, water vapor can condense. Rain falls upon dark volcanic landscapes. Imagine the sound. After the silence of space and the violence of planetary collisions, liquid water strikes rock beneath a heavy atmosphere. Steam rises from hot surfaces. Rivers begin finding low ground. Basins fill. By more than 4 billion years ago, liquid water may already exist on Earth's surface. Tiny zircon crystals preserved in ancient rocks provide clues suggesting surprisingly early interactions between crust and liquid water. Their interpretation continues to be refined, but they hint that young Earth may have cooled faster than older pictures suggested. This does not mean the planet was peaceful. Large impacts still occur. Volcanoes release gases. The young sun behaves more actively than the modern sun in several ways. The atmosphere bears little resemblance to today's oxygen-rich air, yet oceans can persist. There is an intriguing problem here. The young sun was less luminous than it is now. Basic stellar evolution indicates that it produced substantially less energy during Earth's early history. With a weaker sun, Earth might seem destined to freeze. Geological evidence nevertheless indicates long-lived liquid water. This is the faint young sun paradox. Greenhouse gases probably helped keep early Earth warm enough, but scientists still investigate the exact atmospheric compositions and climate feedbacks involved. Even the first chapters of Earth's climate remain partly unread. Then chemistry becomes biology. Exactly how life begins is unknown. No surviving record identifies one location, one pathway, or one decisive moment. Researchers investigate possibilities involving hydrothermal environments, shallow pools, mineral surfaces, chemical gradients, and networks of increasingly complex organic molecules. At some point, systems capable of heredity and evolution emerge. Life exists. The earliest evidence is difficult to interpret because ancient rocks have been heavily altered. Claims for extremely early traces of life sometimes generate intense debate. More secure evidence shows that microorganisms were present billions of years ago. For most of Earth's history, life remains microscopic. This is worth remembering whenever human beings describe Earth as our world. Microbes had an enormous head start. Some organisms eventually develop forms of photosynthesis that release oxygen. Cyanobacteria become particularly important. At first, much of the oxygen reacts with iron and other materials rather than accumulating freely in the atmosphere. Ancient oceans record this chemistry in banded iron formations. Eventually, roughly 2.4 billion years ago, atmospheric oxygen rises dramatically during the Great Oxidation Event. For many existing organisms, oxygen is not a friendly improvement. It is chemically aggressive. Earth's transformation creates opportunities for some forms of life while placing severe pressure on others. A biological waste product begins remaking an entire planet. Nothing comparable is known with certainty anywhere else in the solar system. Venus provides the most unsettling comparison. It is nearly Earth's size and probably formed from broadly similar inner solar system materials. Today, its surface is extraordinarily hot. Its atmosphere is dominated by carbon dioxide and produces immense pressure. Clouds containing sulfuric acid cover the planet. Yet ancient Venus may have been very different. Some climate models allow the possibility of temperate conditions and surface water during parts of its early history. Other models suggest that Venus may never have developed stable oceans comparable with Earth's. Researchers still debate these possibilities because direct evidence from the ancient Venusian surface is limited. Whatever happened, Venus and Earth followed radically different paths as the sun brightened and planetary environments evolved. Venus entered conditions that produced an extreme greenhouse climate. Water vapor reaching high atmospheric regions could be broken apart by solar radiation. Light hydrogen escaped more easily into space. The planet became increasingly dry. Two similar-sized worlds became a blue ocean planet and a cloud-covered furnace. Mars offers another path. Today it appears cold, dry, and thin-aired. Its surface, however, preserves ancient valleys, deltas, lake beds, and minerals formed through interaction with liquid water. Early Mars possessed environments where water flowed across the surface. You could once have stood beside a Martian river. The air would still have been hostile to you, but the landscape might have looked surprisingly familiar in places. Mars is small. Its interior cooled more quickly than Earth's. Its global magnetic field largely disappeared early, Although patches of ancient crust preserve magnetic signatures, its atmosphere gradually thinned through several processes, including loss to space. Liquid water became increasingly unstable at the surface. Some froze underground. Some became locked within minerals. Some escaped. Mars transformed into the cold desert observed today. Whether life ever emerged there remains unknown. That question will eventually send fleets of spacecraft toward the red planet. Mercury follows another extreme path. Close to the Sun, it experiences intense temperature variations between day and night. Its heavily cratered surface preserves an ancient appearance. Yet radar observations and later spacecraft measurements reveal water ice hidden inside permanently shadowed polar craters. Even the planet nearest the Sun can preserve ice. The solar system enjoys undermining simple expectations. Farther outward, the giant planets evolve with their enormous families of moons. Jupiter's moon, Io, becomes the most volcanically active world known. Heated by tidal flexing caused by Jupiter's gravity and orbital interactions with neighboring moons. Europa follows a quieter but perhaps more intriguing path. Beneath its icy exterior lies strong evidence for a global salty ocean. Jupiter's gravity flexes Europa internally, supplying heat that helps keep water liquid beneath the ice. Saturn's moon Enceladus hides another ocean. Jets erupt from fractures near its south pole, spraying water-rich material into space. A spacecraft can sample that material without drilling through kilometers of ice. Titan, Saturn's largest moon, develops a thick nitrogen-rich atmosphere. Methane clouds drift through its sky. Liquid hydrocarbons form lakes and seas on its surface. Water ice behaves there almost like rock. These discoveries belong to a much later human age, but the worlds themselves have been evolving quietly for billions of years. They complicate an old assumption. A habitable environment does not necessarily require a planet sitting beneath warm sunlight like Earth. Tidal heating can sustain buried oceans far from the Sun. The search for possible life therefore spreads beyond Mars. It reaches Europa. It reaches Enceladus. Perhaps it reaches other hidden oceans still poorly understood. Meanwhile, Earth continues changing. Complex cells appear. Multicellular organisms eventually evolve. Life moves through oceans, onto land, and into the air. Continents shift. Ice sheets advance and retreat. Species appear and disappear. Asteroid impacts occasionally interrupt the biological story with spectacular efficiency. One impact about 66 million years ago contributes to a mass extinction that eliminates all non-avian dinosaurs and many other organisms. Mammals diversify afterward. Much later, one lineage develops unusually capable hands, complex language, and an inconvenient tendency to ask questions. Humans appear. Eventually, you look upward. The circle closes. The species studying Martian valleys and European ice is made from material forged before the solar system existed. Its planet formed through collisions. Its oceans emerged from ancient chemistry. Its breathable atmosphere was profoundly altered by earlier life. And now that life has built instruments capable of leaving Earth, for thousands of years, humans could only watch the planets. Then telescopes turned them into worlds. Soon rockets will make them destinations. The solar system is about to be explored from the inside. In October 1957, a small metal sphere begins circling Earth and quietly changes humanity's relationship with the solar system. Its name is Sputnik 1. You can imagine standing outside beneath an autumn night while radio equipment receives its simple repeating signal. The sound is modest. There is no grand orchestral announcement, only electronic pulses arriving from something humans have placed beyond the atmosphere. For thousands of years, astronomy depended upon light traveling toward Earth. Now an instrument can travel outward. The change is enormous. The first spacecraft remain close to home, but ambitions quickly expand toward the Moon, Venus, and Mars. Early attempts frequently fail. Rockets explode. Communications disappear. Spacecraft miss their targets or stop functioning before completing their missions. Planetary exploration develops through persistence, rather than effortless technological triumph. The Moon naturally becomes the first major destination. Robotic probes photograph its surface and demonstrate that controlled landings are possible. Then, in July 1969, Apollo 11 carries humans onto another world. You descend toward a landscape without air. There is no wind. No smell reaches you through the sealed suit. Fine lunar dust lies beneath your boots, while sunlight produces harsh contrasts between brightness and shadow. Earth hangs in the black sky. The view reverses humanity's oldest astronomical perspective. For the first time, people stand on another world and look back at their own planet. Apollo astronauts eventually return hundreds of kilograms of lunar material. These rocks become scientific archives. Their chemistry and ages help reconstruct the Moon's volcanic history, ancient impacts, and relationship with Earth. Decades of increasingly precise laboratory measurements strengthen the broad case that the Moon formed after a giant impact involving the young Earth. A journey through space has become a journey into deep time. Venus receives robotic visitors too. From Earth, its clouds conceal the surface, allowing earlier observers to imagine oceans or tropical environments beneath them. Spacecraft destroy those pleasant possibilities. Measurements reveal crushing atmospheric pressure and temperatures hot enough to melt lead. Soviet Venera landers achieve something extraordinary by surviving long enough to transmit information from the surface. Imagine the scene they encounter. The sky is thick and hazy. Light filters through dense clouds. The ground consists of dark rocks beneath an atmosphere pressing with immense force. The spacecraft survives briefly, then heat wins. Mars offers a different surprise. Early telescopic observers had sometimes interpreted dark markings as vegetation or artificial channels. By the 20th century, romantic visions of an inhabited Mars still linger culturally. Mariner 4 passes Mars in 1965 and returns close images. The photographed terrain is cratered and apparently desolate. Mars initially seems almost moon-like. Later missions complicate that first impression. Mariner 9 enters orbit in 1971 and reveals enormous volcanoes, canyons, channels, and evidence of a far more geologically diverse planet. Viking 1 and Viking 2 land in 1976. Their cameras show reddish soil beneath a dusty sky. Their biological experiments search for evidence of life. The results prove difficult to interpret. Most scientists conclude that Viking did not provide convincing evidence for Martian organisms, although aspects of the experiments remain debated. The question stays open. Later orbiters, landers, and rovers transform Mars into the most intensively explored planet beyond Earth. Sojourner rolls across the surface in 1997. Spirit and Opportunity arrive in 2004. Curiosity lands in 2012. Perseverance follows in 2021. Each carries instruments more capable than those of earlier generations. You begin reading rocks remotely. Minerals reveal ancient water. Layered sediments preserve environmental changes. Deltas mark places where rivers entered lakes. Mars was once wetter. Whether it was consistently warm, intermittently warm, or dominated by cold conditions with occasional melting remains an active scientific question. Ancient Mars refuses to provide one simple climate. Then humanity reaches the giant planets. Pioneer 10 passes Jupiter in 1973, followed by Pioneer 11. Voyager 1 and Voyager 2 arrive later in the decade. Their cameras reveal worlds that telescopes had reduced to colored disks and tiny points. Jupiter becomes turbulent. Its atmosphere contains bands, storms, and complex moving structures. The Great Red Spot appears as an enormous atmospheric system rather than a decorative oval. Its moons are even more surprising. Io is covered with strange colored terrain. Then, active volcanoes are discovered. Material erupts high above the surface. The energy comes largely from tidal flexing, caused by Jupiter's gravity and orbital relationships among the moons. Europa appears smoother. Its icy surface is crossed by long fractures. Later observations strongly support the existence of a global ocean beneath that shell. Ganymede turns out to be larger than Mercury. Callisto preserves an ancient, heavily cratered surface. Jupiter is almost a miniature planetary system. Voyager then reaches Saturn. Its rings resolve into extraordinary complexity. What looked like several broad bands from Earth becomes thousands of structures shaped by gravity, collisions, and orbital resonances. Small moons sculpt gaps and edges. Wave patterns move through ring material. The rings are not solid. They consist primarily of countless particles of water ice, ranging enormously in size. Exactly when Saturn's main rings formed remains uncertain. Some evidence has suggested they may be relatively young, while other models allow older origins with continuing evolution. The argument is not settled. Saturn's moon Titan appears hidden beneath orange haze. Voyager cannot see its surface clearly. Decades later, the Cassini spacecraft and its Huygens lander transformed Titan into one of the strangest landscapes known. In 2005, Huygens descends through the atmosphere. You can imagine falling beneath orange clouds toward an alien surface. Wind moves through a nitrogen-rich atmosphere. Channels and rounded objects below resemble features shaped by flowing liquid. But the liquid is not water. At Titan's temperatures, methane and ethane can rain from clouds and collect in lakes and seas. Saturn holds another surprise. Cassini observes enormous plumes erupting from Enceladus. The spacecraft flies through some of them. The particles contain water, salts, organic compounds, and other materials associated with a subsurface ocean. A tiny, icy moon has become one of the most compelling places to investigate potentially habitable chemistry. Voyager 2 continues farther. In 1986, it reaches Uranus. The planet rotates almost on its side, producing extreme seasonal geometry. Its atmosphere looks relatively subdued in Voyager's images, though later observations reveal more activity. Its moons display fractured and varied surfaces. Then in 1989, Voyager 2 passes Neptune. The planet is blue and dynamic. Powerful winds race through its atmosphere despite the small amount of sunlight available at that distance. Triton reveals an icy surface and active plumes. Then Voyager turns outward. No spacecraft has returned to Uranus or Neptune since those brief encounters. Much of what you know about both giant worlds still rests upon observations gathered during a few extraordinary days. Other spacecraft pursue smaller bodies. Giotto passes Halley's Comet in 1986 and images its dark nucleus. Later missions encounter additional comets and asteroids. In 2005, Deep Impact deliberately sends an impactor into Comet Tempel 1, so scientists can study material excavated from beneath its surface. Humans have progressed from fearing comets to intentionally hitting them. This is an unusual form of intellectual development. Then sample return missions go further. Stardust brings particles from Comet Wild 2 back to Earth. Japanese missions Hayabusa and Hayabusa 2 return material from asteroids Itokawa and Ryugu. NASA's OSIRIS-REx returns samples from asteroid Bennu in 2023. Primitive material can now be studied directly inside terrestrial laboratories. Some grains preserve chemistry dating almost to the solar system's beginning. Human instruments have traveled billions of kilometers to retrieve pieces of the ancient disk described earlier. Another spacecraft heads toward Pluto. When New Horizons launches in 2006, Pluto is still officially called the ninth planet. Later that year, the International Astronomical Union adopts a definition that classifies Pluto as a dwarf planet. The decision produces scientific discussion and an impressive quantity of public emotional attachment. Apparently, planetary taxonomy can become personal. New Horizons reaches Pluto in 2015. Instead of a dead, monotonous ice ball, it finds mountains of water ice, vast plains of frozen nitrogen, atmospheric haze, and evidence of surprisingly complex geological processes. Pluto's large moon, Charon, also displays varied terrain. The distant frontier is active. Meanwhile, Voyager 1 and Voyager 2 continue outward. Both eventually cross the heliopause, the boundary where the solar wind yields to the surrounding interstellar environment. They become humanity's first functioning spacecraft to enter interstellar space in this particular sense. Yet they remain gravitationally within the Sun's enormous domain for a very long time. You now look back toward the solar system through robotic eyes scattered across enormous distances. Mars has rovers. Orbiters circle several worlds. Spacecraft have landed on a comet and an asteroid. Samples from primitive bodies rest inside laboratories on Earth. The planets are no longer merely destinations. They are historical evidence. And beyond Neptune, telescopes are revealing an entire population that earlier astronomers never knew existed. The frontier has moved again. You now return to the darkness beyond Neptune, where sunlight has weakened into a distant brilliance and the familiar planets lie far behind. For most of human history, nobody knew this region contained anything except occasional comets passing through it. Even after Neptune's discovery, the outer solar system remained largely blank. Then Pluto appeared in 1930. Clyde Tombaugh found it by comparing photographic plates taken on different nights and searching for a point of light that changed position. The work demanded extraordinary patience. You can imagine sitting beneath dim illumination while repeatedly examining crowded star fields. Thousands of tiny points remain fixed. One moves. That movement reveals another world. Pluto was initially believed to be considerably larger than it actually is. As measurements improved, estimates of its mass steadily declined. The discovery of its moon Charon in 1978 helped astronomers determine the system's mass more accurately. Pluto turned out to be small. That did not make it unimportant. It made the surrounding darkness more interesting. During the 1990s, astronomers began discovering additional icy bodies beyond Neptune. More followed. The region became known as the Kuiper Belt, named after ideas concerning populations of small bodies in the outer solar system. Its historical naming is somewhat messy because several researchers contributed to earlier concepts. Astronomical terminology occasionally preserves simplified histories. The Kuiper Belt contains remnants from planetary formation. Some occupy relatively stable orbits. Others are controlled by resonances with Neptune. Pluto itself follows a particularly elegant resonance, completing roughly 2 orbits for every 3 completed by Neptune. Their paths are arranged so that the planets do not simply wander into one another. Gravity creates structure within apparent emptiness. Then astronomers discover larger and more distant objects. Quaoar, Sedna, Haumea, Makemake, and others expand the inventory. In 2005, the discovery of Eris intensifies an awkward question. If Pluto is a planet, should Eris be one too? And if similar bodies continue appearing, how many planets might eventually join the list? The debate leads to the 2006 definition that places Pluto, Eris, and Ceres within the category of dwarf planets. Not everyone accepts the definition enthusiastically. Planetary scientists continue debating which classification systems are most scientifically useful. Nature, unsurprisingly, has expressed no preference. Sedna creates a deeper mystery. Its orbit carries it enormously far from the Sun, while keeping it unusually distant, even at its closest approach. Known planets cannot easily explain every feature of such extreme orbits. Other distant objects also display intriguing orbital patterns. This leads to one of modern solar system astronomy's most famous unresolved possibilities. Perhaps another large planet remains undiscovered. The proposed object is often called Planet 9. Models suggest that a distant massive planet could help explain clustering observed among some extreme trans-Neptunian objects. Other explanations remain possible. Observational biases may contribute to apparent patterns. The gravitational effects of populations of smaller bodies have also been explored. Researchers continue searching. No Planet 9 has been confirmed. This is an important distinction. A mathematically interesting possibility is not the same thing as a discovered world. You have seen this pattern before. Neptune was predicted through gravitational effects and then observed. That historical success makes another predicted planet especially tempting. But the solar system does not owe astronomers a sequel. The farthest regions remain difficult to survey because objects there receive little sunlight. A distant planet could appear extremely faint and move slowly against background stars. Large modern surveys improve the chances of finding hidden bodies, while powerful telescopes repeatedly map enormous areas of sky. If another major planet exists, patience may reveal it. If it does not, the absence itself will constrain models. The outer frontier contains another population that remains even more elusive. Long-period comets approach the Sun from many directions. Their orbits suggest that an enormous reservoir of icy bodies surrounds the planetary system at vast distances. This hypothetical region is called the Oort cloud. You cannot point a telescope toward it and see a bright shell. Its members are too small, dark, distant, and widely separated. Instead, astronomers infer the cloud from the trajectories of comets entering the inner solar system. Passing stars and the gravitational influence of the Milky Way may occasionally disturb distant objects, sending some toward the Sun. The solar system, therefore, has no simple wall. Its planetary region fades into distant populations, while the Sun's gravitational influence extends far beyond Neptune. Even defining where the solar system ends depends upon what boundary you mean. The heliopause marks a boundary in the solar wind. The gravitational domain extends much farther. There is no sign saying you have left. Occasionally, the traffic moves in the opposite direction. In 2017, astronomers detect a small object traveling through the solar system on a trajectory showing that it is not gravitationally bound to the Sun. It becomes known as Oumuamua. For the first time, humanity recognizes a macroscopic object arriving from another planetary system. Its properties prove puzzling. Its brightness changes strongly as it rotates. Its trajectory shows a small, non-gravitational acceleration. Comet-like outgassing offers plausible explanations, but no obvious dust-rich tail was observed. Researchers have proposed several natural models involving unusual volatile materials, shape, or surface processes. Its exact nature remains uncertain because it was discovered only after passing close to the Sun. Speculation sometimes races far beyond the available evidence. That is another old human habit. A mystery is an invitation to investigate, not permission to choose the most exciting answer. A second confirmed interstellar visitor appears in 2019. Comet Borisov behaves much more recognizably like a comet. It develops a coma and tail while approaching the Sun. Its chemistry provides a rare sample of material formed around another star, observed without humanity traveling there. The boundaries between planetary systems are therefore permeable. Small bodies can be ejected. Some wander through interstellar space for millions or billions of years. A tiny fraction pass through another star's domain. Our own young solar system almost certainly expelled many objects during its gravitational rearrangement. Some may now be drifting between distant stars. Meanwhile, astronomy has discovered that planets themselves are not rare. In the late 20th century, confirmed detections of planets around other stars finally arrive. The field of exoplanet astronomy grows rapidly. Some worlds are detected because their gravity makes their stars wobble. Others pass across their stars and produce tiny reductions in brightness. Additional techniques reveal still more. Thousands of exoplanets are now known. Their diversity transforms theories of our own solar system. There are giant planets orbiting extremely close to their stars. There are compact systems containing several planets inside orbits smaller than Mercury's. There are worlds larger than Earth, but smaller than Neptune, a common category strangely absent from our own planetary family. Our solar system is no longer the only example available. It becomes one data point among thousands. This comparison forces new questions. Why did Jupiter remain far from the Sun? Why is there no close-in super-Earth here? How common are systems resembling ours? Did Jupiter's migration protect the inner planets, disrupt them, or simply reshape them? Researchers still debate many of these questions because planetary systems can reach similar outcomes through different histories. Modern instruments also transform the search for life. Space telescopes measure exoplanet atmospheres. Radio telescopes investigate cold gas and magnetic environments. Large ground-based observatories use adaptive optics to compensate for atmospheric distortion. Spectroscopy extracts chemistry from faint light. Gravitational wave observatories detect disturbances in spacetime from distant compact objects, expanding astronomy far beyond ordinary light. These discoveries belong to a cosmic scale larger than the solar system, yet they change how you interpret home. Black holes and expanding spacetime remind you that the Sun is one ordinary star inside a far larger universe. Dark matter appears to dominate the gravitational mass of galaxies. Dark energy is associated with the accelerating expansion of the universe. Neither is required to explain your morning sunrise, but both redefine the cosmic environment in which the solar system exists. The old journey from Earth-centered cosmos to modern cosmology has become almost absurdly large. Still, some of the most compelling questions remain nearby. Does Europa's ocean contain chemistry capable of supporting life? What lies beneath Enceladus's ice? Did Mars ever host living organisms? Could preserved samples reveal an answer? What chemistry survives inside primitive asteroids and comets? And are there undiscovered worlds waiting beyond Neptune? You stand beneath the modern night sky. To your naked eye, it looks surprisingly similar to the ones seen by prehistoric observers. Venus shines. Mars glows red. Jupiter appears steady. Saturn remains a small point. The revolution is hidden inside what you now know those lights to be. You have watched them become gods, omens, mathematical wanderers, planets, destinations, laboratories, and records of an ancient disk. Yet the story is not finished. The Sun itself is changing. Its brightness slowly increases. The planets continue exchanging gravitational influences. Moons drift. Orbits evolve. Nothing in the solar system is permanent. To complete its history, you must travel in the only direction humanity cannot explore with archaeology. Forward. You begin the final journey beneath a sun that appears almost perfectly constant across a human lifetime. Morning follows morning. Seasons repeat. The planets return to familiar regions of the sky, and the solar system seems reassuringly permanent. It is not. The Sun is changing even now. Deep within its core, hydrogen nuclei fuse into helium under immense temperature and pressure. That fusion releases the energy that eventually reaches Earth as sunlight and warmth. Yet the accumulation of helium gradually alters conditions inside the Sun. Over immense spans of time, its luminosity increases. The change is far too slow for you to notice during a lifetime, given hundreds of millions of years. However, it becomes important. Earth receives increasing solar energy. The long-term response of Earth's climate is complicated because continents, atmospheric chemistry, biological activity, and the carbon cycle also evolve. Still, the broad problem is unavoidable. A brighter sun eventually makes Earth less friendly to complex life. In roughly 1 billion years, increasing solar luminosity may contribute to conditions that severely reduce the planet's habitability. Exactly when different forms of life become impossible remains uncertain. Researchers model several possible climate pathways, and the timing depends upon assumptions about atmospheric feedbacks and geological processes. There will probably be no single afternoon when Earth simply becomes uninhabitable. Habitability will retreat gradually. Complex ecosystems may disappear before the most resilient microorganisms. The blue planet will change. As temperatures rise over longer timescales, more water enters the atmosphere. Water vapor strengthens greenhouse warming. High atmospheric water can be broken apart by solar radiation. Hydrogen then escapes relatively easily into space. Earth may eventually lose much of its ocean water. The world that once followed a different path from Venus begins moving toward its own hotter future. Long before the sun dies, the Earth you recognize is gone. Mars also experiences the brightening sun. Although extra sunlight does not simply restore its ancient rivers, its atmospheric inventory, surface chemistry, gravity, and geological evolution have changed profoundly. Farther outward, icy worlds may temporarily experience warmer conditions. Regions currently frozen beyond recognition could enter new thermal regimes. Yet these possibilities depend upon atmospheric and geological details that remain difficult to predict across billions of years. The outer solar system will not simply become a pleasant replacement for Earth. Then the Sun approaches a more dramatic transformation. Roughly 5 billion years from now, hydrogen in its central core becomes depleted enough to alter the balance that has supported the star through most of its life. Fusion continues in surrounding regions. The Sun's outer layers expand enormously. It becomes a red giant. You watch the familiar star swell across the sky. Mercury will almost certainly be engulfed. Venus is also expected to disappear inside the expanding Sun. Earth's fate is more complicated. As the Sun loses mass, Earth's orbit can expand outward. At the same time, interactions with the swollen solar atmosphere and tidal effects may pull the planet inward. Current models often suggest that Earth will probably be engulfed, although details of late solar evolution create uncertainty. Even survival would be symbolic. Earth would already be a sterilized, scorched remnant. The oceans would be ancient memory. Continents would no longer resemble anything from human maps. The Moon's story changes as well. Today, it moves gradually away from Earth because of tidal interactions. This recession will not continue unchanged forever. The evolving Sun and Earth's changing rotation complicate the distant future of the Earth-Moon system. Long before every theoretical tidal endpoint is reached, solar evolution transforms the environment entirely. Jupiter and the outer planets have better prospects for physical survival. As the Sun loses mass, their orbits expand. The weakening gravitational grip allows them to travel farther outward. Their moons remain bound unless later disturbances interfere. For a time, increased solar luminosity during giant phases could dramatically warm parts of the outer system. The exact conditions would change rapidly on geological timescales. Nothing remains stable for long. Eventually, the Sun sheds much of its outer material into space. Expanding gas surrounds the exposed stellar core. From far away, the structure may appear as a glowing planetary nebula, despite having nothing specifically to do with planets. The name is another historical fossil. Early telescopic observers thought some of these objects resembled planetary disks. At the center remains a white dwarf. This stellar remnant contains roughly a substantial fraction of the Sun's original mass, compressed into something approximately Earth-sized. Fusion no longer supports it in the familiar way. The white dwarf begins an extraordinarily long cooling process. The surviving solar system enters darkness. Jupiter, Saturn, Uranus, and Neptune may continue orbiting the remnant Sun, now farther away than before because of solar mass loss. Asteroids and comets will also be disturbed. Some objects may be thrown into new trajectories as stellar evolution changes gravitational relationships. Others could approach the white dwarf closely enough to be torn apart. Astronomers already observe polluted white dwarfs containing heavy elements that likely came from disrupted planetary material. In this sense, telescopes can study possible previews of our own system's remote future. Other planetary systems have already reached the ending, ours still awaits. Yet even the surviving planets may not remain forever. The Milky Way is not empty. Stars move relative to one another. Over enormous timescales, some pass closer to the solar system than others. A sufficiently close stellar encounter could perturb distant comets strongly. Across much longer intervals, repeated encounters may alter planetary orbits. Some planets could eventually be ejected. Others might remain bound to the white dwarf for astonishing durations. Predicting exact individual outcomes becomes increasingly difficult because gravitational systems can exhibit chaotic behavior. Tiny differences today can become important after enough time. Scientists can describe probabilities more confidently than precise destinies across extreme timescales. The distant Oort cloud is particularly vulnerable. Passing stars and the gravitational field of the Milky Way already influence it. Over billions and trillions of years, many distant objects can be stripped away. The solar system slowly dissolves into its galactic environment. There is no dramatic border crossing. It simply becomes less complete. Even now, the process works in both directions. Interstellar objects pass through. Solar system objects can escape. The distinction between one planetary family and the surrounding galaxy is never absolute. And somewhere inside this enormous future lies the question humans naturally ask. Will anyone see it? No scientific evidence can tell you whether humanity, our descendants, another terrestrial species, or some entirely different civilization will witness even a tiny fraction of these changes. Human history occupies an almost invisible interval compared with stellar evolution. Recorded astronomy spans only thousands of years. The sun's remaining life is measured in billions. That contrast is difficult to feel. So return briefly to the first fire beneath the prehistoric sky. Someone looks upward. They do not know Earth rotates. They do not know that Venus is a planet or that Jupiter possesses moons. They cannot imagine Neptune. The solar system seems like a pattern of lights attached to a mysterious heaven. Thousands of years pass. Babylonian observers record those lights. Egyptian sky watchers connect celestial cycles with time and season. Greek thinkers turn the heavens into geometry. Aristarchus allows Earth to move. Hipparchus measures the stars. Ptolemy builds a mathematical geocentric cosmos capable of surviving for centuries because it genuinely predicts what observers see. Medieval astronomers preserve that knowledge, test it, criticize it, and improve the measurements. Copernicus moves Earth around the Sun. Tycho measures with extraordinary precision. Kepler replaces perfect circles with ellipses. Galileo raises a telescope. Jupiter gains moons. Venus reveals phases. Saturn eventually gains rings. Newton connects the falling object in your hand with the moon above your head. Herschel discovers Uranus. Mathematics points astronomers toward Neptune. Spectroscopy reveals chemistry in distant light. Radioactivity gives rocks ages. Meteorites carry the solar system backward to a cloud of gas and dust. Spacecraft carry human instruments outward again. The journey has come full circle. The solar system was discovered twice. First, nature built it from ancient stellar material through gravity, collisions, chemistry, and time. Then a species on one small planet reconstructed that history from moving lights, rocks, equations, instruments, and curiosity. There are still missing pages. Scientists do not know exactly where every planet formed. The full migration history of the giant planets remains uncertain. The origin of Earth's water is still being refined. The first emergence of life remains mysterious. Possible biology beyond Earth remains undiscovered. Planet 9 may exist, or the distant patterns may ultimately require another explanation. Even familiar worlds preserve enormous unknowns beneath clouds, ice, rock, and atmosphere. The uncertainty is not a flaw in the story. It is part of the story. Every generation has inherited a sky containing more questions than answers. The difference is that your questions are now informed by everything earlier observers managed to learn. You know the lights are worlds. You know the worlds have histories. You know the sun itself has a beginning and an ending. And you know that the atoms making your body participated in this history long before there was an Earth beneath them. The night can now become quiet again. You no longer need to follow every orbit. Let Jupiter continue its slow journey beyond the window, whether you are watching or sleeping. Let Saturn carry its rings through the darkness, far beyond them. Neptune moves almost imperceptibly, while frozen bodies travel through regions where sunlight is only a distant glow. The moon continues outward by tiny amounts. Earth turns gently beneath you, and the sun carries the entire system through the Milky Way, just as it has done throughout every human night. For a little while, there is nothing left to measure. The ancient sky remains overhead. The planets keep moving, and you can simply rest beneath them.